Everybody, it's a pleasure to introduce our first speaker, Shiri Artstein from Tel Aviv University, and she will tell us about convex caustics and Minkowski billiards.
Hi. So let me start by thanking the organizers for inviting me to give this talk and for inviting us all to this beautiful location. I need my pointer. So I should add this word of caution that I am not a Finsler geometer. I work in convex geometry, but still I was invited, so I'm going to give you a talk about something which is called Minkowski billiards, which is somewhere in between classical Euclidean billiards and Finsler billiards, which are more sort of. And I hope you will find this interesting. And even in this case, and even in Euclidean billiards, actually, there are many, many interesting and open questions, which maybe you can attack. I should also say that this most of what I will talk about is based on two joint projects, one with Yaron Ostrover, who is your chair today, and Roman Karasev, and then the part about caustics is joint with Dan Florentin, Daniel Rosen, and also Yaron Ostrover. Okay, and I chose to so the title is about caustics, but since Minkowski billiards are interesting in their own right, and I think that it's worthwhile to understand what they are in depth, that actually a big part of the talk will be dedicated just to Minkowski billiards, what they are, why they're interesting to study, and some results about Minkowski billiards. And then in the second part, I will talk specifically about caustics. Okay. Right, so I'm going to start with the most basic thing, which you probably all know, but it's always nice to remember, and that is Euclidean billiards. Okay, so Euclidean billiards, the model is that you have a billiard table, which is so I will talk about convex billiards, some convex body K in Rn, so this is n-dimensional space, and here it is. And you start at a certain point. You have a kind of a point mass which travels in straight lines. So you have a point and a velocity. And it travels in straight lines and reflects at the boundary according to the standard mirror law. So even to begin with, you have this point x in the boundary of k and the velocity which has to point towards inside the interior of k. So the velocity has to have scalar product, negative scalar product with the normal at x1. And then when the point hits the boundary, it reflects with respect to a mirror law, the standard mirror law. So here it's drawn over here. So you have the inward velocity and the outward velocity. Think of them as unit vectors. And then the difference between them has to be in the direction of the normal, had to be parallel to the normal. Or in other words, the velocity, the only part of the velocity which changes is the part which is in the direction of the normal. And it just takes the minus sign. So this is this equation of reflection. Okay, this is a very standard thing. And then also very classical is it actually, okay, and then you continue until you hit a point x3 and so on and so forth, and you get a billiard trajectory, a classical Euclidean billiard trajectory in a convex body. This can be n-dimensional, okay, it doesn't have to be two-dimensional at this point. And it's also very classical that the reflection law actually corresponds to critical points of a length functional, and this is here Euclidean length, these, where was that? Here. Okay, so this denotes Euclidean length. Okay, so if I fix x1 and x3 and then I let x2 vary on the boundary of k, then critical points of the sum of these two lengths, these exactly will be the legal billiard trajectories, so these will respect the reflection law. Okay? Please stop me if there are any questions. This is this kind of a talk, I hope.
So assume the boundary is smooth?
Yeah, so for this exposition right now, I'm assuming the boundary is smooth. If it's not smooth, then you have to make some decisions. So you have to decide, for instance, if it's a polygon, what happens when you hit a vertex? One option is to terminate the billiard trajectory and say, okay, you stop there. Another option is to allow it to reflect with respect to any of the normals that you have at that point. So there are various options. But for now, for this discussion, let's assume that everything is very smooth. We will have to change this a little bit later. Okay, and more generally, if you have endpoints, then when you extremize the sum of these distances, then you get a legal billiard trajectory. And already this allows allows Birkhoff, when he studied this model, he was promoted this model, and this is his results from 1913, that under these convexity and smoothness assumptions, just like you mentioned, there exist many, many periodic trajectories, infinitely many, and you can prescribe rotation numbers and so on and so forth. Okay? Okay, now already here you see that I'm using Euclidean distance, and it's very natural, at least in this crowd, to ask what happens when you change the notion of a distance, when you change the way you measure length. For instance, to a Finsler metric, or less generally to just a different norm instead of Euclidean norm. Okay, and this is called Minkowski billiards, and this is what I will speak about. But before that, let me just mention that there are many, many, many intriguing questions, many of them are open, about convex billiards, even in the Euclidean case. Okay, now I'm going to present a list here. It's not exhaustive, and also it's very hard to mention all of the existing results because this is a very vast subject, and I risk, forgetting somebody or something. So let me just mention this very, very briefly. So one of the intriguing questions is simply the existence of orbits if you, for instance, talk about a polygon. So you don't want it to hit the vertices, and then even in a triangle, in a general triangle, it's unknown whether a periodic orbit exists. It's known for certain triangles, of course. For acute triangles, this is a classical result by Fagnano, so Italian, but unfortunately not from Pisa. I hoped he was, but he wasn't. But also for rational triangles, if the angle is at most 100, this is a result of Schwarz. So many things are known, but the general case is open. And this is really funny, right? Because it's so simple to state this question, and yet it's not solved. Then there are questions about integrability. There are various ways to define integrability, so let me not delve into this. I will mention a few things when I talk about caustics later, but this is the famous Birkhoff conjecture, which sort of says that if your billiard is integrable, it has to be an ellipse. And some results, of course, are known. There's a famous result of Bialy, which says that if it's foliated by invariant circles, then it has to be a disk. Then there are questions about shortest periodic trajectories. I will say something about this later. Specifically, you can ask what can you say about this length. You can try and compare it with the volume, for example, or other things. You can talk about the whole length spectrum, all of the lengths of various periodic trajectories that you get, and ask whether this determines the table. Talk about the rotation numbers. If it's in 3 dimension, you can ask whether the orbits are knotted and so on. So many, many different questions, and very little is known. Okay, there are known results, but a lot of things are open. You can talk about strange paths. So the way I defined it, you can imagine a path which actually converges to the boundary because it has infinitely many hitting points which converge to a point. This does exist. This is a result by Halpern, but these are very strange bodies. So if you assume enough smoothness and strict convexity, then this cannot happen. And there are various questions related to caustics. I will speak about some of them in the caustic part of this talk. And then there is another beautiful thing, which is the analogy with a semi-classical limit, which is some kind of a Dirichlet problem talking about its eigenvalues in the plane. And then there are analogies that can be taken between them, and some of them work and some of them don't, and most of them it's not known. Okay, so these are this is a non-exhaustive list of questions related to billiards, and all of these questions can similarly be asked for different billiard law, so for Minkowski or more generally for Finsler metrics, but I will concentrate mainly because of who I am, I will concentrate on Minkowski billiards. Okay, so let me define Minkowski billiards. The definition is exactly the same as before. You have a convex body, you have a point mass, it travels in this convex body, but now you imagine that the convex body is not filled with, is not empty, okay, but it's filled with some medium, and you assume that this medium is anisotropic, meaning that if you think of this as light or whatever, then the velocity depends on the direction, okay, just like Minkowski geometry. Okay, and this means that, but notice that I am assuming that it's a homogeneous, liquid crystal, let's say. So at every point, these velocities, it's the same. Okay, so it's the same material always, but still the velocity of your point depends on the direction. Okay, so this means that within the convex body you will move in straight lines, okay, because these are geodesics for Minkowski geometry, but when you hit the boundary, then you'll have a different reflection law. Okay, so the reflection law actually extremizes not the sum of the Euclidean distances, but the sum of this different distance, okay, subject to the point belonging to the boundary, and this distance belongs to some other norm. Okay, now for my later convenience, I will assume that actually the norm is the norm associated with the body T polar, or the norm is a support function of a certain convex, centrally symmetric convex body T. I could just call T dual, call it by a different name, but this you will see that later for duality purposes, this is actually the thing that turns out most beautiful. Okay, but this is just a notation. So I'm going to say that this is a billiard trajectory in which the geometry is governed by the convex body T, or by the norm, which is the support function of T. Okay. Again? No, so T is a different convex body which determines the geometry. I'm assuming that T is centrally symmetric. You can lose this assumption, but for simplicity, let's assume that. Okay, yes, but I have one body which is the billiard table, and then a different body which governs the geometry. Okay? So you get a different reflection law. It really gives you, so x3 will be different than what it was in the Euclidean case, generically. And of course, similarly, you can do it with many points. So this n is not the dimension. I should have called it m. Okay, so you extremize this sum of the norms, and you get various billiard trajectories. So you can use exactly the same reasoning I mentioned before to show that there are many, many billiard trajectories. And I will call these t billiard trajectories in K. Okay, so there are Euclidean billiard trajectories, and these paths I will call t billiard trajectories.
And now, excuse me, about t, you assume, you have to assume t to be strictly convex, maybe, or not. Otherwise, maybe there is your variational problem has more than one solution. I mean, I'm just worried about this.
Yeah, so just so that we don't worry, let's assume that, okay? Some things can be done, so smoothness is not always needed, but for this discussion. Strict convexity, yes. See, it's the dual, so smoothness and strict convexity of T and T dual are, they interchange. But let's assume that it's great, okay? So it's smooth and strictly convex, so that I'm not worried, okay? And I should say that this whole question, this whole direction was promoted in this beautiful paper of Gutkin and Tabachnikov, where they studied these Minkowski billiards, and actually Finsler billiards in general they study and have some results, but specifically for this case of Minkowski billiards, they have many results, and some of them I will mention. Okay? More questions about the model? Maybe. Okay. So now I want to understand the reflection law, because I said something very abstract, but I want to understand how exactly, what is the reflection law at the point. And to do this, I actually want to go back to Euclidean billiards, because we understand them so well, and think of them in a different way. Okay? And then that way will be easier to understand in the Minkowski setting. So thinking about Euclidean billiards, there are many different ways. So each mathematician prefers to think about it in his own way. So let me mention a few and then say my favorite one, which I want to promote here. So one is the classical Birkhoff way of thinking of it as a discrete dynamical system. So you start with a point and a velocity, and you look at the next hitting point. This is a discrete map between these pairs of a point and the boundary of K, and a direction in the, well, actually it's the open half sphere if we're in high dimensions. Okay? But then there is another also classical way to think of dynamical system, which is as Hamiltonian systems. Okay, so you have a certain Hamiltonian, and I'm going to take it to be half p squared, the moment squared, plus a potential. Okay, and you have this Hamiltonian equations, which the particle has to satisfy. And I want the potential to force my body to stay within, to force my point mass, to stay within the convex body. So I'm going to make the potential 0 on the convex body and plus infinity outside. Okay, so if I do this, then it's easy to see that when I'm inside the convex body, it will travel in straight lines, and it will not get outside. Okay, but the problem is, of course, that these equations, they don't make sense for this potential, because it's not differentiable at the boundary of K. So what you have to do is you have to use approximations. Okay, but then things at this point where you approximate, then things become harder to analyze. So this can be done, and there are several results that come out of this point of view. But for us, it was not sufficiently clear what's going on to be able to prove the results that we wanted. Okay? And then a third way, which I just mentioned here because of what I heard in this conference, it's not really a way that I'm too familiar with, but it is to think of billiards as limits of geodesic flows on K, which is slightly inflated. So you take K, which is in Rn, and you put it inside Rn plus 1. So if K is flat, and you add to it, say, a little ball. Okay, then you have these two surfaces on which actually the geodesics are just straight lines, but you also have this boundary where the point mass actually turns and goes to the other side, so you also have a kind of doubling effect, and you study geodesic flows on this, and from this you can get certain results regarding billiards as limit cases when epsilon goes to 0. So this is another point of view, but the point of view that I would like to promote here is what we call the symplectic approach. So in the symplectic approach, you again go to Hamiltonian systems. Okay, so we choose a Hamiltonian, but now it's not the same Hamiltonian as before. This Hamiltonian is actually non-smooth. It's going to be the norm associated. So it lives in phase space. It lives in R2n. Okay, and it's going to be the norm associated with the product K in Rn in the Q coordinates and the Euclidean ball. I'm still talking about Euclidean billiards. The Euclidean ball in the other n coordinates. Okay, so this is a valid norm. It's only the only problem is that it's non-smooth. So it has these on the product of the boundaries, it has a non-smoothness. Okay, but still you have a Hamiltonian. It's a legal Hamiltonian. You can look at these equations, and when it's not differentiable, you can look at the subdifferential. Okay, and you can ask for this point P dot Q dot or Q dot P dot to belong to the normal cone or to this transformation of the normal cone. So you still get a system. And you can try and solve it. The level sets of this Hamiltonian are very simple, right? It's exactly the boundary of this body over here, of k times b. So this boundary has two components. One is the boundary of k times b, and the other one is k times the boundary of b. Okay, and of course, they intersect in the product of the boundaries. These are the problematic points in which the Hamiltonian is non-differentiable. Okay, but then you can do just Hamiltonian dynamics on this. And let me show you what comes out when you do this. Okay, so the dynamics I claim is rather easy to describe. So let's look at this. So this will be where my dynamics goes on, okay? But I'm gonna my points are gonna be either inside K and in the boundary of B, or inside B and in the boundary of K. This is my level set. This is where the dynamics happens, okay? Okay, so let's start with a point. I'm starting with a point Q1, P1, okay? And I have to look at the differential of H at this point. Now, the problem is that when I start at this kind of a point, H is not differentiable. So let's assume that Q1 is a little bit in the interior of K, just to be safe at this point. So if Q1 is in the interior of K, then actually the maximum is attained for norm P, right? And that means that the differential of H, Q will change because there will be a derivative, but P dot will actually be 0 because Q doesn't play any role when it's inside there. Okay, so P1 will stay at the same place and Q will start moving, and where will it move? Well, since P, I'm taking the usual Euclidean norm, then it will move exactly in direction minus the normal at P, which is P itself. Okay, so I'm looking at the normal of P. In this case, because it's a Euclidean ball, this is just P, P1. And Q will move in the direction which is minus the norm of P. It will, the equations will stay the same until Q hits the boundary. Okay? When it hits the boundary, again, H will not be differentiable, but it's not hard to see that if you look at this differential occlusion, the only tangent vector with respect to which you can move is the one which goes in the direction of the normal of Q. Okay? So suddenly P will not participate in this equation. P will move and Q2 will remain the same. Okay? And then P1 will actually move in direction of the normal of Q. Now this is not Q anymore because this is just some convex body. So P1 will move. Q will stay in the same place. So in some sense, if I'm just looking at the billiard table, then time stopped. If I'm looking at the projection on the billiard table, I had a trajectory, then it stopped. Something is happening now in the phase space. Okay, the velocity is moving. It's moving in the direction of the normal until it hits the boundary. Then you have a new normal, and now Q2 will move in the direction minus of this new normal. Okay? Now from this picture, because it's a Euclidean ball on the right-hand side, it's easy to see that this normal is exactly in the direction P2 minus P1. Okay? And remember that this green line was parallel to the normal at Q, so you get the standard reflection law over here. Okay, so this is just a different way of thinking about the standard reflection law on billiards as dynamical system in this phase space where you have the surface of K times B. Okay, and you can continue. I'm not sure. No, I didn't continue, but you can continue with this, of course, and you get so what you really get is you get two trajectories. Okay, when you look at the picture like this, you get a red trajectory in the convex body K, but you also have a green trajectory which lives inside the convex body B, inside the Euclidean ball. Okay, and like I said, it's easy to see that this gives you the standard reflection law, but what's also not difficult to see is that if you have a closed orbit, okay, so assume that you started the billiard in such a way that the orbit closes, then the red closed orbit will have the same length as the green one. Okay, so something is going on. Now, when I say the same length, I have to be careful. So this length is measured according to the Euclidean length, which is extremized. But here I'm measuring the green path with respect to the support function of K. This is what turns out to be the thing that works out. So here I'm going to have a billiard, okay? And actually it will be a Minkowski billiard in the definition I mentioned before. So the green path will extremize the sum of the HK, of the support function of K, okay? And if I have a closed orbit, then the sum of the Minkowski length of the green path will be equal to the sum of the Euclidean length of the red path, okay? So this is a geometric way to think about Minkowski billiards, and you see that we lifted them, and actually together with the Minkowski billiard, I always get a dual trajectory. Inside So this is not still a Minkowski, sorry. Together with the Euclidean billiard, I always get another billiard in the Euclidean ball, but with respect to a different geometry, with respect to the geometry governed by k polar, governed by the support function of k. And this is why I use the support function of k in the definition of Minkowski billiard. Okay? So again, exactly the same thing, like, yes?
To clarify, when you talked about the dual dynamical system, both are, the lengths are still both Euclidean lengths, right?
No. So here I'm measuring Euclidean length in a general sort of convex body. Let's assume that k is symmetric so that everything works out when in my next sentence. And here my table is round, but the geometry is the geometry governed by k. Okay, and I should have drawn k symmetric because, I wanted Minkowski billiards to be with respect to a symmetric norm, although it does also work on the non-symmetric case. You just have some,
Okay, and so I guess I do follow the argument. Is there a quick way of seeing how? How are the two dynamical systems related?
So the green path, okay, the directions of the green path on the right are exactly the directions of the normals at the hitting points. Okay, so it turns out that these things fit together.
Okay.
Exactly, and I try to explain it, but it's actually something that's easier to understand for yourself on a piece of paper. It's very easy.
I've somehow heard the word Minkowski, and that
yes, that's just my, my issues with saying Minkowski all the time.
Presumably, this then completely carries over. This viewpoint completely carries over to Minkowski.
Yes. Yes, indeed. So this was my next slide. So this carries over. I will, use your wording, which is probably better than mine. This completely carries over to the Minkowski case. So now you can look at the phase space on the body, which is k times t. K and t will be centrally symmetric convex bodies for simplicity. You have the Hamiltonian. You look at the dynamics, and you get exactly the same thing. So you move exactly with the same laws that I just explained. You start with the point. Let's do this. So you start with the point Q1, P1. You move in Q1 with the direction minus the normal of P1. You get to Q2. You look at the normal here, and P now moves. So Q stays at the same place, but P1 moves to P2 in the direction of this normal. You get to P2. You look at the normal. You move in minus this direction until you hit the boundary, and so on and so forth. Okay, this is the dynamic system actually in the phase space on the surface of this product of the bodies. Okay? So this is a way to think about Minkowski billiards. Okay, and again, if you look at this path in 2n dimensions and assume that it's closed, you look at its projection onto the q coordinates and measure its length with respect to the norm, the support function of t. If you look and you compare it with the total length of the green path of the projection onto the p coordinates with respect to the support function of k, and these two lengths are the same. Okay, they are always the same for a closed path. And why, right? So a natural question would be to, let's see, why? But this is actually very simple, because what I just explained is that Minkowski billiards are actually projections of closed characteristics in the phase space. Okay, so there's a general theory, right? You consider a convex body in R2n. You assume that it's smooth because then everything is simpler, but then you can use approximation to get what I was just discussing. You look at the boundary. The boundary is actually the level set of some Hamiltonian, let's say the norm associated with sigma or the norm squared, it doesn't really matter. And then you look at Hamiltonian dynamics. So you look at what are called closed characteristics. These are paths on the boundary of the surface, on the boundary of sigma, which satisfy the following law. So gamma dot has to be j times the normal at the point gamma, and j is just, well, if you think of complex coordinates, it's just multiplication by I. But in real coordinates, you just switch the q and p coordinates and put a minus sign on the p coordinate. So this is the differential equation that gamma has to satisfy for it to be considered at all. Okay, so you have a vector field, and you look at characteristics of the vector field. Okay, and you look at closed characteristics. And one should say that even the fact that there exist closed characteristics on such a domain is non-trivial, but it's a theorem, Weinstein-Rabinovich. And once you have closed characteristic, once you have a closed characteristic in your hand, then you can look at what is called its action. Okay, so in symplectic words, this is the area spanned by a disk for which this this path is the boundary, but you can write it in coordinates just like this. So there should be a half over here. So integral of gamma j gamma dot. This is called the action of the path. And then if you move to the so this is called the action of the path. It's a kind of symplectic way of measuring the area spanned by the path. But then there are two different ways to, there are many different ways to choosing a primitive and computing this action. And if you go back to the dynamics that I explained before, so this is actually why this action is actually this length that I mentioned. So either the length of the projection onto Q or the length of the projection onto P.
Closed trajectories.
Yes.
Otherwise, there's no reason for this.
Yes. I have to talk about closed. If they're not closed, I can still average something and get some equality, but this is more difficult to state. Okay. So what we have discussed so far is that actually you can think of classical billiards and Minkowski billiards as these closed characteristics on the surface, but the surface is not smooth, so we have to be a little bit careful, but it's not very difficult to be this careful. So instead of a differential equations, you will have a differential inclusion. Okay, so instead of a normal here, you'll have a normal cone, and then you won't ask for equality, you will ask for gamma dot to belong to the normal cone. Okay, but once you do that, the differential equations, you can talk about their solutions, they always have solutions, and so on and so forth. Okay, so why is this point of view so useful? Why am I saying that? Well, why am I saying that this is a good point of view on billiards, on Minkowski billiards? So one thing that this helps us study is the shortest Minkowski billiard trajectory in a convex body. So I denote this for a general surface in R2n. I denote C of sigma, the infimal action of a closed characteristic on this convex body. This is called the Eckland-Hofer-Zender capacity of the convex body sigma. Let me mention, so what we realize is that if sigma is k times the Euclidean ball, then this C will be the length of the shortest periodic billiard trajectory. And if sigma is k times some other centrally symmetric convex body, then this will be the length of the shortest T billiard trajectory. Okay, and by symmetry, we said that this is equal to the shortest periodic k billiard trajectory in T. So we have this kind of duality between the two points of view, which is nice to have here. But this object is actually well studied in symplectic geometry, this capacity C. It's called the Eckland-Hofer-Zender capacity, like I mentioned. And it satisfies properties of being what is called in symplectic geometry a symplectic capacity. Now, I'm not going to talk about symplectic geometry over here right now, okay? But capacities are families of functions which have very useful, good properties. And I'll just flash them at you. So capacities are, so this now I'm talking about a general C. C will be called a capacity if it's monotone, it has to be symplectic invariant. Let's not discuss this. It has to be too homogeneous, so volume is not a capacity. It has to have a specific kind of homogeneity. And then there is a normalization, which is that the capacity of a ball and the cylinder, which includes this ball, but it has to be a symplectic cylinder, okay? They have to coincide and they equal to pi. Okay, so a priori, just looking at this set of axioms, it's completely unclear that any capacity exists, that any symplectic invariant really exists. But this is a celebrated result of Gromov, that they do exist. So Gromov constructed, the smallest and the biggest symplectic capacities, which are more or less the biggest ball the radius of the biggest ball you can put inside your convex body symplectically, or inside your set symplectically, and the radius of the smallest cylinder into which you can embed your set. And the fact that these are actually capacities and are normalized is due to this non-squeezing theorem, this celebrated theorem of Gromov. So I'm not really going to explain anything more about this. I'll just say that once Gromov defined these capacities, many other capacities have been discovered, and one of them is exactly this one, which I described to you. Now, I described it to you on convex domains and has a different description, or various other descriptions if you want to talk about general sets, but for convex domains, this is exactly this capacity, and it satisfies all of these properties. Okay, and when you realize that your length of billiard is actually a well-studied object, you can use everything that's known about this object. So one thing that is known about the Eckland-Hofer-Zender capacity comes from something called Clark dual action principle. Let's not discuss it in depth, but it's actually just a formula. It's a formula to compute the capacity, the Eckland-Hofer-Zender capacity of a set, the minimal action of a closed orbit. And this is a very simple formula if you look at it, okay? It only involves the support function of the convex body. Here it's the square of the support function. You minimize something connected with this function on some loop space. So all loops which are centered and have action 1. Okay? So this is a formula. But already from this formula, you can see something. So first of all, the formula itself, not like what I described before with the differential equations, which I had to change to an inclusion. This formula makes sense immediately also for non-smooth convex bodies. Okay, so you can just use it as your definition. Another thing that's very transparent from this formula is monotonicity. Okay, so if sigma is included in sigma 1 is included in sigma 2, then the support functions of sigma 1 is less than the support function of sigma 2, and thus this functional will be bigger for the bigger body, for the body which includes. Now this is completely unclear for biliard trajectories, right? So from this you get, because this capacity is the length of the shortest periodic biliard trajectory, you get that this function, the length of the shortest periodic biliard trajectory in K, is a monotone function of the body. But of course when you change the body, then the reflection law completely changes, and there is no reason to think a priori that this number should be monotone, but it is. Another thing that you get from this formula, so this is from some previous work together with Ron Ostrover, is, well, we had to modify this formula a little bit to have a power 1 there, but once you have a power 1 and you know that support functions are additive with respect to Minkowski addition, okay, which is sort of trivial, then you get a Brun-Minkowski type inequality. So you get that the capacity of the sum of two sets, and this is Minkowski sum, okay? So sigma 1 plus sigma 2 is just x plus 1, x in sigma 1, y in sigma 2. Right? So this is a very linear operation on convex sets, and capacity, these actions or these biliard trajectories, they're very nonlinear sort of creatures, but still you have this kind of Brun-Minkowski type inequality for symplectic capacity. This was quite surprising at the time. Okay. Now, once you have this Brun-Minkowski, then again, this interpretation that the capacity is actually shortest periodic biliard trajectories gives a Brun-Minkowski type inequality for these lengths. Okay, so I'm denoting here by psi b of k, the shortest periodic Euclidean biliard trajectory in k. I just said that it's the capacity of k times b, and then you get this Brun-Minkowski inequality. So the shortest periodic biliard trajectory in the sum of two bodies is more than the sum of the lengths of the shortest trajectories in each of them. Again, this was completely unexpected. And of course, it's not important that it's a Euclidean ball. The same holds for Minkowski billiards, where now you are looking at the length with respect to t. And here there's also symmetry, so you can either measure the length with respect to a sum of bodies. So you can either change the Minkowski geometry to be the Minkowski geometry of the sum of the bodies, or you can change your table to be the sum of two tables. And in both cases, you get a Brun-Minkowski type inequality. Okay. Okay, and one other result, and I know that I'm supposed to talk about caustics, I will, but one other result which I want to mention, which this point of view brought to life, was related to what I mentioned at the open question at the beginning, was related to bounding by the volume the shortest trajectory. Okay, and this is because there is a very famous open conjecture of Viterbo from 1991, it's actually for general capacity, so not just for this specific capacity I mentioned before, but let's think about that one because I didn't define any other one. And it says that the capacity satisfies an isoperimetric type inequality. So of all convex bodies of a certain volume, the one with largest capacity is the Euclidean ball. Okay? The Euclidean ball in two n dimensions. Remember, we're now living in somehow in the phase space. Right? So it's not any of these billiard trajectories that I mentioned, the billiard bodies that I mentioned before, although some of them are symplectomorphic to the Euclidean ball, surprisingly enough. Okay, so this is a conjecture. I copied it here. Okay, and without convexity assumption, it's simply not true. Okay, so you can find non-convex sets for which this is not true. For some capacities, of course, I didn't define my capacity for non-convex sets, so this statement doesn't make so much sense in this right now. There is a stronger conjecture, again, I have to mention it, which is that all capacities, so if you want to satisfy these four axioms, there's actually just one way to do this if you're thinking of convex domains, and this is a stronger conjecture, actually. So again, I'm not explaining exactly why. Viterbo proved his conjecture up to a factor which depends on the dimension and grows like n, like the dimension, using this tool from convex geometry called John ellipsoid. Some of you probably know it. And in a work already maybe more than 10 years ago, together with Vitaly Milman and Ennio Nostrover, we proved that Viterbo's conjecture holds asymptotically. What does that mean? There is a universal constant for which this kind of inequality holds. So if all you want is like order, magnitude of the growth, then you have it here. Okay? But the question whether gamma can actually be brought to equal 1, this is still an open question. Okay? But using this in our interpretation of capacity as shortest billiard trajectories, you immediately get a bound for the shortest t billiard trajectory in K, a bound which is a volume bound depending on the volume of K on the volume of T. Okay? Now actually this bound is not very exciting for symmetric convex sets because, it's true also for non-symmetric, yes. Because actually we showed, and this is this work that I mentioned at the beginning together with Roman Karasev and Ennio Nostrover, we showed that, let me put one more, we showed that there is actually a formula for this capacity for the shortest billiard trajectory, for the shortest t billiard trajectory in K, or K billiard trajectory in K, which is this 4 times the in radius of t polar inside K, or in the special case where the two bodies are K and K polar. Okay, the polar body is the unit ball of the support function. Yeah. So for this specific body, the capacity is equal exactly 4, no matter what K is. Now I'm saying that it's exciting, but it doesn't look very exciting. It just says that something is 4, and from this you can deduce the second line actually follows from the first line by one more line. But why was it exciting for us? It was exciting because it implied something in convex geometry. Remember, I come from convex geometry. That's really my goal. This is why I'm studying all of these things. And this very simple fact, which is actually quite natural, because if you think about the billiard interpretation, then what happens here is that you play a billiard in a convex body K, and the geometry is the norm of K, right? It's a support function of K polar, so it's the norm of K. And then you have these very simple billiard trajectories. Let me draw them here. So this is, let's say, K, and then you have K polar over here. And you have very simple billiard trajectories, which are just 2 bouncing trajectories. So you have the normal over here and over here. They come, I don't know, I probably won't draw it correctly like this, but something like this, okay? And this is a closed orbit. And it has length 4, because you go back and forth. This is exactly 4. Okay, and you have actually, it's foliated by these paths. So in every direction, this is actually a valid path. So this is not a very surprising result that this equals 4. But we were extremely happy because if you plug just this result into Viterbo's conjecture, which I remind you relates the capacity with volume. Now the volume of the product is just the product of the volumes, right? And if you use Viterbo's conjecture, if you assume that it is correct and you plug it in, you get this bound for the volume of K times the volume of the polar of K. And this is a very well-known open problem in convex geometry, whether for centrally symmetric convex bodies, the volume product, so the product of the volume of K and the volume of K polar, is minimized by a cube and its dual, a cube and L1. There are actually more than one minimizing bodies, so a cube and L1, also L1 and a cube, of course, but there are also all these Hanner polytopes which are also minimized, which are also conjectured minimizers. And this problem is completely open in n larger than 3. And actually the case n equals 3 was solved very recently, just something like a year ago, I think, something like that. Okay, so this gave us a very strong connection between symplectic geometry, Viterbo's conjecture, and convex geometry, which was, well, fun, at least. Yes, I don't really have time to explain this, but there is a more elementary approach to shortest periodic trajectories promoted by Bezdek and Bezdek. So it's, yeah, I don't know. Really don't have time for this. Let me just say it because it's really beautiful. So it says, okay, you want to compute the shortest periodic trajectory. What you have to do is you have to look at all points, all sets of points which you cannot put inside your body altogether. So there is no translation of K such that all of these points are in the interior. Okay, just look at this family of points, and now look at the sum of the. Order them in any way you want, okay, in some kind of order, and sum up the distances, okay, in a cyclic way. So the last one here is xm minus x1, okay, and then minimize. And the family of points which give you the minimum is its length, the length of the trajectory that you get is exactly this. Will be a billiard trajectory, and it will be the minimal one. Okay, so in this picture, the red points are illegal because they are inside K, but the green and also the blue points are fine because you can't put them inside K. You connect them, you minimize this huge problem, but then what you get is always the length of the shortest periodic billiard trajectory. So this is a completely geometric approach to the same problem. Okay, and I should say, so the blue thing you shouldn't look because actually this carries over to the Minkowski case, and this was noticed both by our student Yoav Nir and by this group in Karasev's sort of group, that this carries over to Minkowski case, and again you have this very nice geometric formula for the shortest periodic billiard trajectory. T billiard trajectory in K, and the minimum is always a 10, so you always have a minimal trajectory with less than the dimension plus 1 point. And from this nice formula, you immediately get something. So monotonicity is immediate, right? Because if K is bigger, then there are less points which you cannot move inside it. And also Minkowski is immediate because the support function satisfies this additivity, and then with the sum you have this sub-additivity. Sub or sub-additivity, whatever, and you get Minkowski very easily from here. What you don't get from here is you don't get this duality. So you don't see in this picture, at least I can't see, if somebody does then it will be very interesting, why when you take this problem and you exchange the roles of K and T, then the answer remains the same. This is completely out of reach from this method as far as I can see. And I remind you that from our perspective, we just have this dual orbit. So for every orbit, there is a dual orbit, and their lengths are the same. So this part is completely clear in this phase space view, Hamiltonian view. Okay? And now I'm getting to the part which was in the title of my talk, which is caustics. So what we wanted to do in this project, which I will now present very briefly, is to take this orbit-to-orbit duality and see what it can tell us about caustics. So is there a duality not only for orbits, but also for caustics? So let me say a few words about caustics, because I haven't mentioned them at all yet. So first of all, what is a caustic? So let me start by talking about the Euclidean case, okay? Things carry over very easily to the Minkowski case. So assume you have a billiard table K, and you have a convex set inside it. When will I say that it's a caustic? It's a caustic if you start a trajectory which is tangent to it, and it keeps being tangent after each hitting point. Okay, this is called a caustic, and I want C to be convex. I insist that it be convex. Okay, so I'm talking only about convex caustics. Now, in 2 dimensions, there's a very famous sort of Poncelet theorem that if you start with an ellipse, if the table is an ellipse, then confocal ellipses are its caustics. Exactly. Okay, so these are these pictures over here. But these are not the only caustics in 2 dimensions. So there is a famous theorem of Lazutkin which says that if you're sufficiently smooth, so you have to be 6 smooth in the current results, and positive curvature, then you always have caustics near the boundary. Okay, so there are always these paths, always these other sets which are very close to your set for which you stay tangent if you start tangent. Okay. If you omit this condition on the curvature, then everything fails. So the minute that you have zero curvature, this is a result of Mather, then you do not have any caustics at all. Okay, even if just one point has zero curvature. And then there is a quantitative version of this result by Gutkin and Katok. And there are many, many open questions, even in the Euclidean case, about caustics, and specifically this Birkhoff conjecture. So how many caustics can you have if you're not an ellipse? So can you have many caustics? This is the very sort of laid-back way of saying this conjecture, and there are many partial results in this direction, which I don't mention because there are, I'm afraid to forget somebody or say somebody that I shouldn't say. And this is really strongly connected with integrability and with ergodicity, because the minute you have a caustic, this means that all paths which start outside will never enter inside. So this really splits your phase space into 2 parts which do not interact at all. And this is supposed to be this picture over here, where the caustic is actually this kind of invariant circle on this cylinder. Okay. Now you notice that I was talking here only about 2 dimensions in most of this slide, although the definition I give it in general. And the reason is that there is a beautiful theorem that I call it Gruber-Berger theorem. So these are 2 independent proofs of the same theorem, which says that the minute you move out of the plane, so you're in 3 dimensions, then there are no caustics. The only option for a caustics is if you are really an ellipsoid, and this is these classical classical theorems. But any other body in 3 dimensions, you will not ever find a caustic for it. Okay? I want to mention here that in this Minkowski geometry, this example that I drew here on the board is exactly an example of a caustic. Of course, it's very degenerate. It's a point caustic, but for Minkowski geometry. So here we have a family. All of the paths which pass through the center, they are all remain tangent to the center. Well, they just continue. They're just 2 bouncing points. So there is some kind of difference. And actually, one of our motivations for this project, this is something we haven't solved yet, or maybe we will never solve, is to understand whether there is an analog of Gruber-Berger theorem for Minkowski. What kind of caustics can indeed exist? And I think this is a very interesting question, so if anybody is interested, has something to say, then please tell me. Now, you can ask, okay, but in 2 dimensions, are there many caustics? Can anything be a caustic? And here I should mention, this is also well known, so maybe this will be easy, that there is this Gardner's construction. There is a way, if you want a caustic of a certain shape, you can always guarantee it. What you do is you take the caustic that you want, you take the set C, and then you put it sort of on your paper, and you take an inelastic. You take a string of length L, you wrap it around the convex body, and then you pull around and you draw whatever you get. So I did this very sort of like this. You get something, you get a closed shape, and this shape will have C as its caustic. Okay, so formally I define I look at all the points in R2 such that when I take the convex hull of the point and my shape, the perimeter is less than L, the length of this string. Okay, this is called a string construction also. This is very classical way of drawing an ellipse, right? So you just take 2 points and put a string and move around, and this draws an ellipse. So an ellipse is constructed like this when the caustic is just a segment. Okay, but you can do it with any body, and you always get this way caustic. So in R2, any body can be a caustic. When you have a caustic, there are some classical parameters that you can measure for it. You can measure the string length that is, and any caustic is constructed this way in R2. So if you have a body and a caustic, then the body is the string construction with some string length. And when you have a caustic of a body, you can measure the string length. There is a rotation number. There is the perimeter of the caustic. These are parameters of the caustic. And I should say about this Gardner's construction, if you think about Minkowski geometry, you can do exactly the same thing. Okay, just the perimeter that you measure here, you measure with respect to your Minkowski norm. Okay, so you have two straight lines, and then you integrate the Minkowski norm of the tangent, and you get again a caustic with respect to Minkowski norm. So this carries over, and this was also proved in this paper of Gutkin and Tabachnikov, that the Gardner's construction works also for Minkowski geometry. Okay, right, and what we asked ourselves is okay. So now assume that you did this Gardner's construction, you got a caustic in Minkowski geometry, you have all these paths which are tangent to it. Okay, let's stay still in the Euclidean case. Then what we said is that we have, for all of these, we have dual paths in the ball, right, in the disk. We have the dual paths, and so do they also have the caustic? Okay, so let me say this again. I'm taking my convex body with a caustic. I'm taking all of the tangent lines. So this is an invariant circle to the billiard map, right? All of these lines have their duals because all of these paths have their dual paths. Okay, so I'm looking at all of these lines. Now they're in the circle. Okay, and I'm asking, well, do they envelope a convex set? Is their envelope a convex set? So this is a very natural question about duality. When you have duality and you have caustic, so this is a question about caustic duality. Okay, so when will I say the two caustics are dual? Let me say it this way. So let's assume that I have a T caustic in K, so a caustic with respect to T geometry in K, and a K caustic in T. I will say that they are dual if all the trajectories, if I start with a trajectory, now it's in two-dimensional space, right? If I start with a trajectory which is tangent, then it remains tangent throughout the motion. Okay, in this case, I will say that the two caustics are dual. Now, it's not hard to show, to check actually, that if you already have dual caustics, then all of these parameters, the perimeter, the rotation number, the string length, they will all be the same. Okay, but notice that now I'm measuring perimeter or string length with respect to the right geometry, okay, to the support function of the other body. Okay, so this is an easily checked fact. And for Euclidean billiards, we were able to show that indeed this duality phenomena holds. So if I have a caustic in the Euclidean, if I have a caustic with respect to Euclidean geometry in K, then it always has a dual caustic inside the ball with respect to the geometry of B. Okay, so this is the theorem with Florentin Ostrover and Daniel Rosen. So Dan Florentin, Yaron Ostrover, and Daniel Rosen. Okay, so it's written here. If the body is centrally symmetric, strictly coordinate C1 smooth. So I do need these restrictions, so probably not really so much. Well, it has to be sort of C1 smooth in order to even have a caustic. Then whenever I have a caustic with respect to Euclidean norm, then I will have a caustic in the Euclidean ball with respect to the support function of K. And this is the picture. Okay, so here I have the caustic inside K, then I will always have a corresponding caustic inside the Euclidean ball. I'm afraid I probably don't have time to say anything about the proof of this theorem, but I should say that it's a constructive proof, so we have a formula. Okay, this is what I planned to say about how we got to this formula, but we have an exact formula for the dual caustic. If I have a formula for my caustic, I can produce a formula for the dual caustic. And if you start with caustics which are polygons, then the body is actually just, we call it an ellipsagon, right? So it just has elliptic arcs. And with ellipses, you understand everything. So this duality theorem is trivial for ellipses. And then you use this in order to understand what your formula should be. And once you have a formula, then it needs some work, but it's not so hard to show that it works. Okay? And so the proof is by explicit construction. Let me just say the last theorem for this talk is that, of course, we asked ourselves, does this hold also for Minkowski geometry? If I have a Minkowski caustic, will it have a dual Minkowski caustic? And unfortunately, here the analogy breaks, and this is no longer true. So there is an example of two centrally symmetric and infinitely smooth sets, K and T, such that K has a convex T caustic, but this caustic does not have a dual caustic. And the way to produce this, the main idea, I will really say it briefly, is actually to take a Minkowski ellipse with respect to L1, with respect to L1 distance. So you actually have to take the dual norm, which is the cube, and then produce an ellipse with respect to the cube. So you have this octagon. And then it's not hard to see that so this octagon sort of has this segment as a caustic. Of course, this is not exactly true because things here are not smooth. So I have to smooth things for it to work. But sort of the idea is that because the caustic is a segment, then if L1 had a dual caustic, it would also have to be a segment. And then you use approximation, and you show that actually the length of the segment that this body will have as a caustic, it has to be very short. But remember, the dual caustic is supposed to have equal perimeters. So this is how you get a contradiction. This is not an explicit construction. We just show that in one of these smoothings, there has to be, there cannot be dual caustics, because otherwise you get some contradiction in the end. So this is not very explicit, but what you can ask is, okay, so I have this family of lines. It has a family of dual lines. It's not convex. The envelope is not a convex caustic. So what is the envelope? Because you always have a non-convex envelope of an invariant circle. You're just not convex. And here, okay, so this needs some more work. But here, the picture turns out that this is what happens in this L1 body, more or less. So you do have a caustic, but you do have an envelope, and the envelope is very far from being convex. And it remains to be understood, which of these two cases is typical. So is it typical that a caustic doesn't have a dual, or is it typical that it does? We sort of conjecture that having a dual actually characterizes Euclidean balls, but yeah, I think that my time is super up, and I thank you all for your attention.
Any questions? Comments?
Yes. I was trying that you won't have time for questions, but it didn't work.
So, what is your feeling about the Birkhoff conjecture extended, if you try to extend it to Minkowski billiards? Does one expect to find more integrable?
This is a very difficult question. I hesitate to even conjecture. I don't really know. It's very hard to analyze what's going on. So you're saying if Birkhoff conjecture is true, do I think it will also be true in?
Or maybe that it's not true if you extend too much.
Yes, I don't know. I think that it should be. investigated. Okay, so the partial results that do exist for Birkhoff conjecture, maybe these can actually be. So there are some partial results that can be translated to Minkowski geometry, very few.
And so, because then a related question: are there pairs of convex sets such that the product is symplectomorphic to, say, ellipse cross ball? Because then this would be, in some sense, another integrable, but in some sense trivial because it's still the same.
It's still, yeah, they are equivalent.
But
I don't know. I would guess that yes, but this is like.
I don't know examples. I would guess.
Maybe
yes.
Our chair knows something.
You don't know, yeah. Okay, thanks.
Did you look at the what was called exterior billiards or the billiards? So is there a similar symplectic description of what's going on there? It's where you trade the angle for the lengths.
Yes,
so
we looked at we actually it's in my next slide.
I see.
Something about exterior billiards, but there. We don't know a kind of dual. So actually, there is not even I think a reasonable notion of Minkowski outer billiard. It's.
Why not? You can define it in the same way because you have tangent. You go twice the length. You just repeat the definition of the outer billiard. It makes perfect sense. You just need to have a notion of length for this.
Yes, so I'm
so it's
finding it hard to recall, but there is some issues there. So the dual, I don't know of this kind of dual representation, but outer billiards are actually also connected to something very interesting in convex geometry, which is to floating bodies. So you can, at least in 2 dimensions, then an outer billiard exactly means that a caustic for an outer billiard means that the caustic is actually the floating body of the, sorry, that now the table is inside, right? So the table is a caustic, so the table is the floating body of the caustic because now the caustic is outside. So you asked if all these trajectories are all have this common, and this is also related to the previous question. So now you can ask these kind of Birkhoff kind of conjectures for floating bodies, which makes sense in higher dimensions. And also there not much is known. So the situation is kind of parallel, but these are almost the same questions. And this is another analogy that one can probably harness, but we haven't done anything in this direction, unfortunately. Guys.
So this pertains to a stronger conjecture that you mentioned in connection with Viterbo's conjecture, which is all symplectic capacities actually coincide for convex sets.
Yes.
Now, this question might probably make no sense, but it's motivated by an interesting phenomenon one sees in the complex geometry of convex open sets. Hence the question. Do we know that among all possible symplectic capacities, there is one that is the smallest capacity for all convex bodies and one that's the largest capacity for all convex bodies?
Yes.
And what are they?
Yes, so I mentioned this very briefly, but without the formula. So it has nothing to do actually with convexity. There is a smallest symplectic capacities among all symplectic capacities that you can define it for any convex body, for any open set. And that is, you just take the radius, pi times the radius squared of the biggest Euclidean ball. You can embed symplectically into your set. Okay, so this has to be the smallest one because of monotonicity, and then there's also the largest one, which is the same thing but with a cylinder from the outside. So these do exist, and for this ball capacity, of course, Viterbo's conjecture is valid because of volume considerations.
Correct. Yes.
Okay, so this is why actually, if all symplectic capacities coincide on convex sets, which is plausible, they can't coincide on all sets, on all open sets, but convex sets, then this would imply Viterbo's conjecture. Okay, this is why it's a stronger conjecture.
Right. Thanks.
Any other questions or remarks?
Yeah, so this is possibly a very naive question. So when you consider the dual body or the polar body, you use the Euclidean structure of Rn, right?
Yes.
And if you don't have a scalar product, your polar body will be in the dual space. And then can you make this billiard construction in just a normed space? Like your base space is just a normed space, not Rn. Can you do billiards in?
So I'm not exactly sure how to answer. I mean, I think that for this model to work, you need some kind of pairing, right? Because you want to move in the direction of the p coordinate, so to speak. So you need a pairing between the two spaces, and this pairing is the same one with respect to which I take the polar. So I'm not sure if I don't have a pairing at all, then if I can even sort of define things. But I don't know. I mean, maybe I'm.
Oh, okay. Yeah.
Okay, I'm really used to having like Rn with a scalar product and not worry about this.
Thanks.
Sure.
Other questions? Okay, so let us thank our speaker again. And we resume in 30 minutes. Okay, so it's a pleasure to introduce our second speaker, Andrea Spiro, and the title of his talk is Finsler Metrics of Complex Domains with Monge-Ampere Exhaustions.
Okay. So first of all, let me thank the organizers for giving me the opportunity to give this talk in this very nice congress. And okay, the contents of this talk is about a recent result that in a joint work with Giorgi Patrizio we obtained on existence of complex Finsler metrics of complex domain with Monge-Ampere exhaustions. The structure of the talk is divided in 4 parts. In the first part I will give a very short summary of the basic definitions of what are the Kobayashi metrics of complex domains, how are they defined, and why they are related with the Finsler metrics and complex Finsler metrics, the topic of this congress. These are elementary definitions that I review mainly to fix the ideas and the notation. Then after this short introduction we will talk about extremal Kobayashi disks, which are basic objects to consider to study the property of Kobayashi metrics and how they are related with the manifolds, with the domains with Monge-Ampere exhaustions. I will give the definition of Monge-Ampere exhaustions and domains admitting that and why they are related with Kobayashi metric. And these are the main object that we will study, the domain which admits this Monge-Ampere exhaustions, because in that case the Kobayashi metric has this very nice properties. And then in the third part we go into the core of our talk. So we will discuss the properties of domains which admits many Monge-Ampere exhaustions, and we will end up with our result, which we call propagation of regularity theorem, according to which it will happen that as soon as a complex domain admits just one Monge-Ampere exhaustion, that it has an infinite number of Monge-Ampere exhaustions, and this automatically implies that the domain is equipped with the natural biolomorphic complex Finsler metric. So according to this result, we have a huge family of complex domains equipped with this natural structure which can be studied using Finsler geometry. And then the very last part, it's just a couple of slides in which I would like to propose some 2 lines of possible research of studies that are motivated by this result, just to give some bridge to the future. So let us start with this talk, and with the very first part, recalling what is the definition of Kobayashi metric of a domain. So consider a domain in Cn, and let us denote by TD with a little knot upstairs the tangent bundle with the zero section excluded. When you will see this little knot nearby the tangent bundle of something, it means that, yeah, I'm taking off the zero section. Now, the Kobayashi infinitesimal pseudometric, shortly pseudometric without infinitesimal, is the map kappa defined on TD with the little knot in the non-negative real numbers, defined as follows. There is this procedure. Fix a vector in the tangent space of one point of the domain, and consider the class of all maps of this kind. So the holomorphic maps from the unit disk in C into the domain, which are holomorphic, that map the origin of C into the point that you prescribed, and such that the tangent vector to the real axis is a multiple of the vector that which you want to compute the Kobayashi metric. So the picture that you must have in mind is the following. You have the unit disk in C and consider all possible maps, which maps the origin into the knot and maps the tangent vector to the real axis to something parallel to your vector. Now, for each such map, lately we call this map disk tangent to V at the point Z naught. Consider the length of V using the push forward of the Poincare metric of the unit disk. You have the Poincare metric of the unit disk, you take the push forward and you consider that on the image of the disk. The vector is tangent to the image, so you can consider the length of this vector with respect to the push forward. Or if you want it much shortly, take the vector, take the pullback by the map, and consider the norm of this vector by the Poincare metric, which at the origin coincide with the Euclidean length. So for each vector, you consider all these possible values, and then you take the infimum of this value. The infimum of this value is the value of the Kobayashi pseudometric on V. I mean, that's the definition of the Kobayashi pseudometric. Now, there are a couple of crucial properties of these functions. There are a lot of properties of this function which are well known, but I just mentioned some crucial ones. One is that this function is distance decreasing in the following sense. If you have a holomorphic map from your domain D to the domain D prime, then the value of kappa at the image of the vector under the holomorphic map is always less or equal than the original value of kappa on V. So automatically you have that if F is bilomorphic, it has the inverse, you can also consider the reverse inequality, and so actually you have this, that this value is actually equal to the value of the kappa at V. So this function is a bilomorphic invariant, and it is canonically associated with your domain. And then by just playing with the definition, you can see that anytime you multiply a vector by complex numbers and you compute the kappa of this lambda V, you have this homogeneity property. So it's equal to the modulus of lambda times kV. Now, these are nice properties, but then there are some discouraging facts, at least for the point of view of differential geometry. I mean, I am a differential geometry, and I like to take derivatives. I mean, a nice word for me is a word which is smooth, on which you can take any derivative you want. But this Kobayashi metric, in general, is not smooth. It's just from the point of view of the differential geometry, is ugly. It's, generically, it's upper semi-continuous. And there are very bad things that might occur. For instance, there are, if the domain is unbounded, you may have vectors which have kappa V equal to 0. And so it's something not pleasant to deal with. And another discouraging fact is that domains in which this function kappa can be explicitly computed are quite rare. You can compute it explicitly, writing the coordinate for the unit ball, for the polydisks, some domains with some symmetry property, but if you take any domain, it's almost impossible to compute. But despite of this the basic definition and implies so many things about the kappa that you have a huge amount of results that can be determined by using the Kobayashi pseudometric. So the for people in several complex variables is an object which is used continuously and gives a lot of information. So this is just to motivate to try to explain why Kobayashi metric is so important for people working complex variables. Now, now let us see the relation between Kobayashi metric and complex Finsler metric. Why I'm talking about Kobayashi metric in this congress. Now let us recall shortly the definition of complex Finsler metric. I give the definition with a lot of nice properties. I mean, a complex Finsler metric on a complex manifold, J is the complex structure of the manifold, is a map defined on the tangent bundle on non-negative real numbers, such that it is smooth on the tangent bundle without the zero section. Of course, one can ask a lower regularity assumption, but let us, in this talk, let us consider only smooth case. This is what we like. Then you want the homogeneity property for multiplication by complex numbers, which is analogous to the homogeneity property for real Finsler metric. So if you take a vector and you multiply by lambda, it's the same of taking the value of a metric multiplied by the modulus of lambda for any complex number. And then the third property is that you want that the indicatrix, so the set of vectors for which the length with respect to this Finsler metric is less than 1, is a strictly pseudo-convex domain into the tangent space that you may identify with CN. The condition of being strictly pseudo-convex is the perfect analog, complex analog of the usual strictly convexity condition that is used when you work with the real Finsler metric. Of course, you can relax this hypothesis. You get weaker definitions of complex Finsler metric. But when I mention here complex Finsler metric, I mean something which satisfies all these hypotheses. Now, why complex Finsler metric entering the game in several complex variables? There are many reasons for that. I just mentioned one which I consider crucial and one to which I'm interested, and it is the following. Suppose that your Kobayashi metric for a domain has the nice property of being C infinity. As I told you, almost never, well, generically it is not, but suppose you're lucky enough to have a domain in which kappa is smooth, and suppose that the indicatrix of kappa is bounded, strictly pseudo-convex at each point. Then automatically you have that 1, 2, 3 are satisfied, and you have that kappa is a complex Finsler metric, and it is, by the way, canonically associated with D, because the construction of kappa is intrinsic, it's a bilomorphic invariant. So in this situation, to consider the Finsler invariance of kappa, by Finsler invariance I mean the Finsler curvature, Finsler covariant derivatives of higher order, and so on, you get a collection of invariants which are biomorphical invariants and which in principle determine D up to biomorphism. If you have all this collection of invariants, you have something which you can use to study D up to biomorphism. And this is one of the crucial problems of several complex variables, how to distinguish domains up to biomorphism. So if you are lucky enough to have something like that, you must be happy. Now let's go into the second part and let's see some bunch of domains for which you have reasons to be happy. And now let us recall shortly the definition of Kobayashi metric. As I told you, is the infimum of all these values, the norm of the pullback by f of the vectors v, where f in the class that I mentioned before. Now suppose suppose that in this class you have some special element for which the norm of the pullback of the vector v is exactly the minimum, not just the infimum, it's just realize the minimum of that. Then in this case, automatically this value coincides with the value of the Kobayashi metric. Now, if you have it, let us call it extremal disk, extremal Kobayashi disk. If such holomorphic map exists, then you can check it depends not on the vector v, but just on the complex direction of the vector v. And the value of kappa along this v is strictly positive for all v in this line, v non equal to 0. So suppose that you are even more lucky that you have a unique extremal disk for any direction. Then what you get? You get a whole collection of disks passing through the points, and they give you what is usually called a singular foliation. It's not a regular foliation because all these disks pass always through the same point. And the leaves of these foliations are the images of these disks. Maybe these disks, after they depart from the center, they can cross again. So, but you have a singular foliation, at least on the neighborhood on this. Yeah.
Excuse me, back on the, maybe I'm sure I missed something on the definition of AZW.
Yeah.
So f star of p over dx is a multiple of v, or it has to be a multiple by a complex number?
No, it must be a multiple, a real number, by a real number here. Yeah, it's it must be a real number, a multiple by a real number. But then, since it is holomorphic, then you can relax the hypothesis and you can rotate. You get the same disk. If you have a disk which has this multiple of this, then if you rotate this by a complex number, you take the same disk, and but before you apply the rotation before starting, and then you adjust you rotate this before going that, and this gives another disk which is attached to the one. So you're right. There. Okay. So I'm saying, so that if you're lucky enough to have an extremal disk for every direction, then you have a singular foliation. And so far, for what I know, the nice example of domains in which kappa is proved to be a Finsler metric are precisely those for which you have such natural foliation of disk. I'm not saying it is a necessary and sufficient condition. I just want to say that if you are lucky enough to have extremal disk for every point, you have a singular foliation. So if you want to have manifolds with nice properties for the Kobayashi metric, consider those which have such singular foliation natural. And in fact, the good domains that I'm going to describe now, that in the next slides we are going to discuss, are domains which have such natural foliations, and you will see that they have a good property for the Kobayashi metric. So the next slide is exactly the definition of these domains that I'm interested in. So let D be a bounded domain with the boundary of smooth class C infinity. The definition I'm going to give here is always C infinity, but you can relax and you have lower regularity. But just for simplification, we work always in the C infinity class. Now, what I call a C infinity Monge-Ampère exhaustion is a continuous exhaustion of the domain with values between 0 and 1 that takes the value 1 exactly on the boundary with these 4 properties. These properties are not, some of them are redundant, some of them can be deduced from the others, but I list all of them so you have a clear picture of what is happening. So you want that the level set tau equals 0 is exactly given by 1 point, which is called the center of this exhaustion. Now you want that outside the center, the exhaustion is of class C infinity, and so in general this exhaustion is C infinity only outside the center, but if you consider the blow up, you want that when you extend it on the blow up, you pull back the exhaustion, and so you have an exhaustion of the blow up, then it becomes smooth on this blow up. Then you want that outside the center, these differential conditions are satisfied. Namely, you want that the 2i dd bar of tau, so the complex action of tau is strictly positive. You want that when you take the log of tau, it is at least non-negative, and you want that the nth power of dd bar log tau is equal to 0. This condition is equivalent to say that when you write in coordinates the complex Hessian, then the determinant of this Hessian is equal to 0. This means that the Hessian has some kernel, some kernel. Now, if you combine C with the property A, and just to write down, it's a simple computation, shows that the kernel of dd bar log tau not only is non-trivial, but it has exactly dimension 1, exactly one dimension. And then because of the second property, that the Hessian is strictly positive, it implies that the level set of tau are strictly pseudo-convex, because this becomes the Levy form of the level set, and so this level set are strictly pseudo-convex. And then the last condition is that you want that the log tau, for sure it goes to minus infinity, because tau at the center goes to 0, so log tau minus infinity. But you want that it goes to minus infinity precisely as the Euclidean distance up to some bounded function. So when I mention the motion per exhaustion, I mean something which satisfies this. Oh, by the way, from hypothesis B and C, one can deduce this that this log tau is the pluricomplex green function of the domain. Every domain for every point has a pluricomplex green function, which is the analog of green functions for harmonic functions. But in general, it has regularity low, at most, in good situations, C11. So requiring that everything is smooth out of this C0, it means it's the same as requiring that this pluricomplex green function is special. It's the...
condition A,
yeah.
That you have a Kähler metric?
Yeah, automatically. It's this tau, the dd bar tau, gives an Hermitian metric, Kähler metric outside. Now, domains which means at least one motion per exhaustions are called of circular type by Patrizio in the first paper, 84.
A singular Kähler metric, right? Since
it's a Kähler metric outside the center, because outside the center is smooth. In the center is almost never smooth. Actually, it is smooth only in the domain.
Oh, it's okay. It's strictly positive.
Okay. Now let us see. Let us see some example, actually, the main two classes of example of these domains to understand what we are talking about. There is a big class of examples which is given by the circular domains. Namely, consider a function on Cn with non-negative real values with the usual homogeneity property for multiplication by lambda, and take this set of points for which mu is less or equal than 1. These domains are the so-called circular domains. You can define the circular domains in another way, but this is equivalent. Every circular domain admits a mu, which is called the Minkowski function of this domain, and so you can introduce in this way. Now, assume that mu is smooth, so that the boundary of D is a smooth function, and assume that the hypersurface, so the boundary of D, the hypersurface mu equal 1 is strictly pseudo-convex. Then you are exactly in the situation that I'm talking about. So you have a strongly pseudo-convex domain, and the function, the square of this of this mu is an exhaustion, which satisfies all nice properties that I was telling you. So when you want to think about one domain with such an exhaustion, think about these things. That's why the domains were called by Patrizio of circular type, because they are modeled on these things. For this exhaustion, there is the particular point which is the origin, which is the one where mu is equal to 0. and it is the center of this exhaustion. So a big class of these domains are given by the circular domains. But there is another very important class of examples, which are the strictly convex domains in Cn. Now, consider a strictly convex domain with smooth boundary in Cn. When I say convex, I mean convex, not pseudo-convex. I mean really convex, considering Cn as the affine space R2n. I mean, that's a convex as in the previous talk. Which is a kind of strange hypothesis in several complex variables, because convexity is not something which is preserved under biolomorphism. So it's for people in complex variables, this convexity is well, it's good, but I mean, since it is not, it depends on how you put this domain in Cn. If you apply a biolomorphism, you ruin everything because it's no longer convex. Now, suppose it is convex. Then, by convexity, you may consider a smooth deformation of your domain into a ball. Think about your domain. By convexity, pick a point. Then you can squeeze smoothly your domain to a ball which is entirely contained into it. So, you may consider a one-parameter family of strictly convex domains. At each stage, it remains convex, starting from the ball, which I designed here, and reaching for t equal 1, the big domain. Now, using the existence of this smooth deformation, Lempert in the 80s proved a lot of results on these convex domains. And I summarize, from these results you obtain the following. You can construct a one-parameter family of exhaustions for all domains of these deformations, which start from the exhaustion of the unit ball, the standard exhaustion. This is the distance of the H point from the center of the ball divided by rho, and this is the classical motion per exhaustion of the ball. And then at each stage, each tau t is still a motion per exhaustion. Actually, you can even compute this, in principle, compute it. There is the explicit definition of tau t is that you have to take the hyperbolic tangent squared of the distance between 0 and w according to the Kobayashi distance. The Kobayashi distance is not the Kobayashi metric. It's related, but it's not similarly defined by it's not the same thing. Anyway, don't focus on that. Think only the fact that you can construct a motion per exhaustion, and so that your domain, your final domain, you get a motion per exhaustion for the domain you are interested in. This construction, given by Lempert, can be done by choosing any point z0 in your domain. And this is a crucial difference between these two classes. If you have a circular domain, you have a natural way of constructing a motion per exhaustion, which is this. You just take the Minkowski defining function, and you have it that the center is 0. If you have a convex domain, take any point, and you can construct a motion per exhaustion centered on this. And this difference between these two classes of example motivated our research. We wanted to find something which intrinsic that distinguish the convex domain from the circular domain. We wanted to obtain some result proving that generically a circular domain has only one exhaustion, and the convex domain have infinite exhaustion. This is where our aim, but we failed because we proved that you have an exhaustion for every point, also for the circular domains. Even if it is not natural to construct, then you have it for all circular domains. And this is what surprised us quite a lot. Now, before going into the result and to describe better what I'm saying, I want to shortly review some common feature of the example A and B and all other manifolds which admit at least one exhaustion. And so remember that the kernel of dd bar of log tau is always of dimension 1. So it gives you a one-dimensional distribution, complex distribution, regular, at least outside the center. And you can take the integral leaves of this. The closures of the integral leaves gives you a singular foliation as the one that I mentioned before by complex disks, all passing through the center Z0 of the exhaustion. In the case of circular domain, the disks, the integral leaves are exactly the straight disks, the intersection of your domain with the straight lines of Cn. For convex domains, the integral leaves are deformed. If it is the ball, you have straight lines. And then when you deform it by that construction, you have these leaves which slide little by little deformed. But still they give a nice foliation of the domain. So we are in a nice situation like the one that I was mentioning before. So maybe if we are lucky, then the Kobayashi metric has nice property. And here is the description. In fact, we are close to what we are looking for, because anytime you take a vector of the tangent space in Z0, there exists a unique proper holomorphic disk, so a map from the closed disk into the closed domains, which image is one of the leaves of the foliation of Z, passes through Z0, and the image of the real of the vector tangent to the real axis is proportional to V for some so f of lambda is proportional to V, as it would be a nice situation. And in fact, Patrizio in the 87 proved that every such disk is extremal for the Kobayashi metric, and the value of the Kobayashi metric at Z0 along the V is exactly the factor here that you have here. And the Kobayashi indicatrix of D is a strictly pseudo-convex domain. So for this situation, you have the two nice properties that you're looking for. The nice property that you're looking for, the fact that the Kobayashi indicatrix is strictly pseudo-convex. So you have immediately the following situation. If D is circular and strongly pseudo-convex, then the Kobayashi pseudometric has a strongly pseudo-convex indicatrix at the center of the exhaustion that we mentioned before. Actually, it is a domain which is linearly equivalent to the domain itself. While if you have a strictly linearly convex with smooth boundary, you have this phenomenon, the phenomenon of before, for every point Z. And so you have the third condition that you need. So in that case, kappa is a Finsler metric, is a complex Finsler metric. So these domains, the complex domains, are nice because the Kobayashi metric is Finsler. The circular domains are not so nice, at least until our theorem was proven, because we need that you have a nice property of a Kobayashi pseudometric only at one point. We don't know if the same happens in all the other points. And our result will be that actually also for these domains, the same thing of the convex domain will hold. Now let's go to the crucial part, the core of the talk, and discuss our theorem. The main idea that led us to our result. So as I told you, our starting point was try to distinguish the example of class A for the example of class B. We were thinking about the example of class B, A, those which has only one exhaustion and one natural exhaustion, and the others with a natural exhaustion for every point. So we started to try to characterize the domain with a lot of exhaustions. So we considered the case in which a domain is a circular type, so it has at least one exhaustion. But assume that there are not one, but at least two distinct exhaustions and two singular foliation passing through two centers. Then what do you have? If you use the properties of this singular foliation and domains admitting the properties of these exhaustions and their singular foliation, you may construct a homeomorphism from the closure of the domain into the closure of the unit ball, which transform the holomorphic disk of the singular foliation into the straight disk of the unit ball. You can always do that. Practically, in the Lampert results, he was constructing explicitly this map from here to here. So the deformation of the domains can be used to deform this disk and put it into the straight form. But this straightening process, you can do it for any domain with the Monchampère exhaustion. It's intrinsic. You can do it. This is the result by Patrizio. And so you have this straightening map. But you can do the same straightening map also for the other center. And both maps are holomorphic along the disk, because any disk is mapped holomorphically into the straight disks. And since everything is smooth outside the center, you may construct this map so that it is smooth outside the center, from the outside Z0 and outside W0. So if you combine these two maps, so you first go from the domain into the ball and then back, you obtain a map which it is more homomorphic from the domain into itself, moving the center Z0 into the new W0. It is holomorphic maps along the disks. It is smooth on the bar, and then there are other regularity properties concerning the extension of the things on the blow up. Now this happens when you have two exhaustion, two centers. Now suppose that you are in the situation of convex domains, and then you have not only just two, but actually for any curve you may have a one parameter family of exhaustions centered at the point of the curve. Suppose that you have so many exhaustions, and so you have a curve, and for each point of your curve you have an exhaustion centered at that point. Then you may repeat the process of before for every pair of points, starting from the first to the point zt. And so you obtain a one parameter family of homomorphism from the domain into itself. All of them are smooth outside the center Z0, and they are extendable in a smooth way at the blow-ups between Z0 and ZT. Then they move the point Z0 to the point ZT, but they always, since they are maps from the domain to itself, the boundary is mapped into the boundary. The restriction of each of such map on the disks of the first foliation are holomorphic, and they map each disk into the disk of the second foliation. And the crucial fact is that the exhaustion of centered at ZT can be recovered from the exhaustion centered at the point Z0 by composing with this phi t. This phi t is constructed in such a way that this is always satisfied. So to have the one parameter family of the exhaustion is the same of having the exhaustion tau naught and all this family of phi t. So you transform the problem of studying the exhaustion tau t, which are the actual problem, into the problem of discussing the phi t. Then, since we want to study this one parameter family of exhaustion, we want to study this, and we associate with this phi t two crucial objects. One is the vector field xt that you obtain one parameter family of vectors defined in this way. You take the derivative with respect to the parameter t and pull it back by the phi t. It's like a Lagrangian, like if you have a fluid and you consider the velocity of this fluid and you pull it back always at the original situation. Lagrangian version of the velocity of a fluid of the velocity field of a fluid. And then also you take the standard complex structure and pull it back by the map phi t. These maps phi t usually are not biholomorphism, are biholomorphism only when restricted to the disks. In the other direction they do not preserve the complex structure. So when you pull it back you have a complex structure but not standard, different from the standard one. Now this pair, the vector field xt, the one parameter family of vector field xt and the one parameter family of non-standard complex structure, we call it a fundamental pair. You will see in a moment why we call it fundamental, because it's crucial in our theorem. Now the pair that we associate with every one parameter family constructed in this way satisfy a bunch of conditions. Now I don't want to tire you to tire you so much. So I didn't write the explicit condition in coordinate. You can do it. All conditions that I'm mentioning here can be written explicitly in coordinates, and you have the explicit conditions. But now, to be short, I just described by words which kind of conditions are. There are some conditions on the complex structure JT, and the main condition is that when they are restricted to the vectors tangent to the disks, they have to coincide with the standard complex structure, because the maps are biomorphic along the disks. So when you pull back the standard complex structure restricted to the disk and you pull it back, you still get the standard complex structure. And then another condition is that if you consider the orthogonal vectors with respect to the Keller metric that you mentioned before, orthogonal to the singular foliation, then it is preserved by this JT. And then there are other conditions on XT to the effect that the restriction of phi t are holomorphic on the disk. Namely, when you restrict this vector field and you take the projection along the direction of the disks, these XT are infinitesimal automorphisms of the disks. So in any case, you can write explicitly these conditions. Another fact, actually the crucial fact, is that the JT and the XT are related by this fundamental equation. So the derivative with respect to t is exactly the Lie derivative of JT with respect to XT. Actually, they have been defined as two objects so that this equation is satisfied. Then you have that each JT, even if it is a non-standard complex structure, it is an integral complex structure because it is diffeomorphic to the standard complex structure. So the Ninehurst tensor of this JT has to be vanished, another differential equation that has to be satisfied. And finally, there are some very important boundary conditions on the boundary of T and the limit behavior of these things when you go towards the center Z0. They due to the fact phi T preserves the boundary. So when you take the derivative, you get the vector fields which is still tangent to the boundary. And also phi T is smooth when you go to the blow up. This means that the Lie derivative, no, the value of XT when you take the limit towards Z0 is blocked. It's a very strange things. I mean, when you use this condition, you see that the value of XT at Z0 is completely determined. It's blocked. It's a boundary condition very strong. Now, by the way, one thing. This limit behavior requires that XT, when it goes when you compute the limit towards Z0, is completely determined by the tangent vector of the curve at the point T. So when you write down this condition, it enters in the expression, it enters the tangent vector of the curve of centers. So now, given a curve ZT, any pair XT and JT will satisfy all these conditions when you write them exactly. Let us call it an abstract fundamental pair, guided by this curve. I mean, when you write these conditions, the curve enters in the game for the condition D. Now, if in case this pair is actually associated with a family of exhaustions, which gives the family phi T, for which this is the fundamental pair, let us call it concrete. So you have a big class of pairs which satisfies the differential equations. And inside this class, there is a smaller class of those which actually comes from a family phi T. I mean, these conditions are necessary conditions for being the pair associated with phi T. So, in principle, this set, the set of concrete pairs, is smaller than the abstract pair. But a crucial lemma that you can prove, I mean, not so easy, but you can prove it. It turns out that these two classes do coincide. So these conditions that I'm writing are not only necessary, but they are also sufficient. So if you have a pair XT which satisfies these differential equations, then automatically you have a one-parameter family of exhaustions for which you construct the phi t, and which gives this pair associated as fundamental pair. That's why I call it fundamental pair. So due to this crucial lemma, to look for domains for which you have a one-parameter family of exhaustions is the same as look for domains for which you have solutions of the problem given by A, B, C, D. So we transformed and what we wanted to do is to show that the circular domain, there are examples of circular domains for which there are no solution of A, B, C, D. If there are no solutions, then you don't have a one-parameter family of exhaustions. But we proved the opposite, that given a domain of circular type, so even the circular ones, and an exhaustion, consider a disk of the foliation and take the point of a segment inside the disk. Then you can show that you have an abstract, which is then a concrete pair guided by the curve ZT. I mean, you don't have any abstraction to the existence of a pair like that. I mean, this is the most delicate point, and it's quite long. I mean, the argument of the proof is basically goes down to the fact that everything boils down to a PDE problem to show the existence of solution of the conditions A, B, C, D, and they are nested. You can take a read of one of the other after everything, and at the end you end up that the whole thing is equivalent to find solutions to a one-parameter family of complex structure, interval complex structure of the kind prescribed in A. So they must be equal to the complex structure along the disks, standard complex structure along the disks, and they have to preserve the orthogonal distribution, which are a solution of this problem, the condition B that I wrote before. This xt is now known, but it turns out that because of the boundary condition, it's always equal to the sum of two vectors, x1 and jtx2, which are independent. They depend only on the vector on the curve zt that you have. This because of those boundary conditions, which are very strong. So it becomes just a one equation on the one-parameter family of complex structure, and because this x1 and x2 depends only on the domain. This equation is non-linear, if you see, because here you have the jt twice. I mean, it's not a linear equation, and this makes a problem. But you can reformulate the problems using deformation tensors, and you can prove the existence of solution. Actually, we proved the existence of solution of this in the lower regularity, not in smooth regularity, but in ck alpha regularity with k larger or equal than 4. And then, since this is for every k and for the uniqueness of the Monge-Ampère exhaustion, then you get the result in this infinity case. Now, if due to this, then, as I mentioned, now we have that if you are in this hypothesis, you have a one-parameter family of exhaustions centered for all points of the segment. Since every point of your domain can be reached by a segment in a disk, then you have an exhaustion for every point of your domain, and this is our result. So suppose that D is a strongly pseudo-convex domain which admits at least one exhaustion, then each other point is center of some exhaustion, because you can reach it by a segment like that, and the dependence of this thing is infinity. So we reach what we wanted when I promised it. So suppose that you have a domain with a Monge-Ampère exhaustion, for instance, a circular domain strongly pseudo-convex, not necessarily a convex domain. Then its Kobayashi metric is a complex Finsler metric as I defined. So we enlarge it. So far, we knew that the Kobayashi metric is Finsler metric for strictly convex domains. But now we know that we have a condition which is really biolomorphic invariant. It's just enough to have a Monge-Ampère exhaustion, and this is a biolomorphic invariant condition. Just a remark, we proved everything we made, the whole setting, not just for domains in Cn, but for complex domains in complex manifold with boundaries. So actually, the thing is really intrinsic. You can consider the result in the larger category. And now here are the last two slides where as I promised, I think that there are at least 2 lines, many of them there are, but 2 lines of possible thoughts. One is the following. Suppose that D is a smooth, strictly linearly convex domain, so those considered by Lampert. Then the theory by Lampert tells that the extremal disks for the given by the Monchampère exhaustions are not only extremal disks, but they are complex geodesics for the Finsler metric. I mean, to be extremal disk means that it realizes the Kobayashi metric at the center. But to be geodesics means that as a real sum manifold of the Finsler metric, it is a totally geodesic manifold, and the disks realizes the Kobayashi metric at each point of its image. Now, our proof that generalized the Lampert results for generic domains of circular type, at the moment, do not say anything about the extremal disk. They say that we may construct the extremal disk, but we don't know if they are complex geodesics or not. I mean, we don't have, maybe there is an easy reason, maybe it's hard, maybe it's not. I mean, we just didn't think about that. I think it would be interesting to study this aspect. So, using either Finsler geometry or several complex variables, I don't know, well, one can try to study the extremal disks of domains of circular types and see if they are necessarily complex geodesic, which is a much stronger property than being extremal, or construct counterexamples, so construct domains for which disks are extremal but not totally geodesics. How to cook up counterexample if one wants. See next slides, which arrives here. This is the next slides, and it is the last slides of the talk. Suppose that D is a domain of circular type, so with the omniting one Monchampère exhaustion. Now we know that there are at least 3 big classes of invariants, which in principle completely characterize the domain up to biolomorphism. One class of invariants is given by the CR invariants, so you see the invariants of the CR geometry of the boundary. If by our hypothesis, if it is everything smooth, is compact, and everything, if you know that 2 domains have the same CR geometry, so the equivalent CR geometry, then they must be biolomorphic. You may extend it into it. And remember that the boundary of D can be considered from the point of view of the Finsler geometry as the point at infinity of the manifold D inside. So you have this class of invariants. Another class of invariants is the so-called blind and Duchamp invariants determined by one Monchampère exhaustion. I mean, it will be very hard to describe what are these invariants in few words. I wrote just a small, a little phrase to mention how they arise, these invariants. I mean, when you have this Monchampère exhaustion, you have this singular foliation, these leaves. And these leaves determine the diffeomorphism between each level set. I mean, you have your domain, you have the center of exhaustion, you have the singular foliation, and then you have the level sets of the exhaustion. Now, this determines not biolomorphism, diffeomorphism between each level set into the next ones. So you may identify all of them from a differential point of view. And for instance, take one of them, take the complex structure, the CR structure on the boundary, and pull it back here. Take this and pull it back here. So you may reduce the problem of discussing these level sets by considering just one of them equipped with a one parameter family of complex structure, which are the one that you pull back by this diffeomorphism. So if you fix one of them and you consider this one parameter family of complex structure, you may look at how they deform. Take the derivative of this and see how they deform. Now the blended Duchamp invariants are determined by series terms of a series expansion of the tensor, which describe how this complex structure changes according to the level set. And I mentioned this because they are very useful to construct examples, because these blended Duchamp invariants are completely parameterized by arbitrary functions. There is by blended Duchamp result. You pick an arbitrary function holomorphic function in a certain space, and then you cook up associated blunt and Duchamp invariants and associated domain. So it's an excellent object to construct example with the prescribed properties of blunt and Duchamp invariants. And we use this in our paper with Patrizia in 2015. Now there is a third class of invariants, which are the Finsler invariants. You may compute the Finsler curvature of the Kobayashi metric and all covariant derivatives. They are tensor field defined on the projective tangent space. So you have this bunch of invariants, all of different nature for the same domain. So I think it would be quite useful to find explicit relation between A, B, and C. There must be explicit relation because they all determine the domain up to biholomorphism. But if one can make explicit relation between these things, then you can use the technique of constructing example with blunt and Duchamp invariants to construct the domains which have a prescribed property for the Finsler geometry or prescribed property for the CR geometry of the domain. I mean, I think it would be very useful to explicit this. And the proof that we made, the fundamental pairs, I think will be very useful to make explicit the relation between B and C. I mean, that's all I needed to say, and thank you for your attention.
Any questions?
Okay, so my class of examples doesn't quite fit your level of regularity because it's only C11, but does Teichmüller space admit Monge pair exhaustion? Teichmüller space with Kobayashi metric does have Kobayashi metric, but it's only low regularity. It's C11. So do you know if it admits the Monge pair exhaustion?
No. Can you repeat once?
Okay, so take Teichmüller space.
Teichmüller space. Okay, no, I couldn't.
Right.
Okay,
it's
okay.
only low, it has only low regularity. It doesn't fit your theory, but still it has plenty of extremal disks, etc., etc. So
okay.
Does it admit the exhaustion? Exhaustion?
The exhaustions of like this Monge pair exhaustions, they
maybe of lower regularity, maybe not.
They do have exhaustion like this of regularity, low regularity. We cannot generalize this result, at least at the moment, no, because we had to solve, to show the existence of many Monge pair exhaustion as we did, we had to solve differential problem. And C11 is so little that...
No, I understand this, but does it have...
No, but there are Patrizio and Abate and Patrizio made papers exactly on what you are talking about.
Okay, thank you.
So could I have a look at the, not the last slide, but the one before that?
This one?
Yes. So I'm not entirely certain of the details, but then I might probably know an example of a domain which is not a generic domain of circular type. Mm-hmm. The Monge, it does have a nice Monge pair exhaustion with all of the properties, but the circularity simply is circle action. It's a reasonably nice circular action in that it's a weighted circular action. The each coordinate is weighted not by the phase, but by powers of the phase.
Okay.
Now, do you think starting with this kind of a guy, one can cook up something to produce a counterexample literally for generic domains of circular type? Is there any scope?
Counterexample to what? Can you
to an actual
to show that
domain of circular type, because in the weighted circular domain that I'm thinking about, the leaves of the singular foliation are extremal, but they are not complex geodesics.
Okay. So you say that it might solve this question?
Yes.
It could be. I mean, really, I mentioned this just to stimulate some thought. Maybe we can think about that. I didn't explore this question in detail. I mean, we just finished the result, so we are just exhausted of the result. And that could be a good idea to pursue. Okay, thanks a lot.
Okay, maybe one more quick question.
These Finsler complex spaces, they are not really Finsler manifolds. Yeah? Is it correct? So that your norms are not necessarily convex?
Yeah. Okay. Your question, your final remark answered it. If the indicatrix is also convex, then they are also real. But you might have a complex Finsler metric in which the indicatrix is not convex. It's strongly pseudo-convex, but not convex. Yeah.
But what is the relation to the Kobayashi metric? Is it I mean, so you have really metric on this, so on your domain. So this Kobayashi distance function. What is the relation of your
the Kobayashi, you're talking about the finite Kobayashi distance. It's the integral. I mean, I'm not because one has to be delicate with the Kobayashi distance because locally it's just integrating the Kobayashi infinitesimal distance. Actually, the Kobayashi infinitesimal distance can be considered as the infinitesimal version of the Kobayashi distance. But globally, you might have strange things because the Kobayashi distance is determined how you take one point and another point, and then you connect the 2 points using several disks, and then you compute the distance along the disk, and you take the infimum. Now, you might have that if you integrate the Kobayashi infinitesimal distance along a curve, you get something which is strictly larger than the value of the Kobayashi distance because but locally, if locally you can connect the 2 points always by just one single disk, then the infinitesimal and the global Kobayashi distance they coincide. So what I want to say that there might be some pathology in spatial domains, but for a starting point of view, consider the infinitesimal Kobayashi distance as the analog between Riemannian distance and Riemannian metric at the tangent space. Did I answer your question?
Yeah.
Okay.
Thanks.
It's maybe also vaguely related to one thing I mentioned in my talk that, okay, you have this way of measuring lengths and it's a scale invariant. And then to obtain the correct Finsler metric, the rule is on each tangent space you take the convex hull of your star-shaped domain. And this gives you a genuine, maybe only contiguous or upper semi-contiguous, but then at least you have a norm or in each tangent space. And I also mentioned that it goes back to Buzman and Meyer, but Kobayashi also wrote a paper on exactly this subject, and I think the point was to make exactly this link. Now I'm not sure. Okay,
thanks.
Thank our speaker again.
So the last talk for today is by Gautam Bharali from the Indian Institute of Science, and he will tell us about the notion of visibility based on the Kobayashi distance and applications.
Thank you very much. And I would like to begin by thanking the organizers of this wonderful conference for giving me an opportunity to talk about some of my work and to just be in such a wonderful city. So thank you very much again. So I'll begin fairly rapidly because it's quite fortunate for me that Professor Spiro explained a lot of what is on this slide. You've actually seen this definition already. I have slightly different notation from what he had, and I'm using what I'd call undergraduate calculus notation over here. The primes here actually stand for the holomorphic derivative. in general, this object, this functional, that at each point on the holomorphic tangent bundle of the domain omega assigns a number, a non-negative number to a vector v, is in general merely a pseudometric. However, whenever this object kappa omega is strictly positive definite for every z in omega, and this happens, for example, if omega is a bounded domain, then this object is in fact a Finsler metric. I must point out this is Finsler in the sense put up on the board by Mark Troyanov on day one. But there is sort of one sense in which this chap is better, in that if I scale v by a complex scalar, then kappa omega of the scaling is equal to modulus of the scaling times kappa omega. So it's in that sense nice, but its irregularity, as Andrea Spiro mentioned to us, is pretty terrible. I actually should have pointed out to you that what we start out with are domains. These definitions are about domains in Cn, which means that given any pair of points, I can actually find a holomorphic disk that will be mapped into the domain omega and hit both of the pair of points of interest in the domain omega. The upshot of which is that the Kobayashi pseudodistance is in fact the integrated pseudodistance associated to this pseudometric. I also want to point out that the original definition by Kobayashi isn't what I have stated over here, but it is in fact a theorem that the Kobayashi pseudodistance is the integrated form of the Kobayashi pseudometric. To sum up in this slide, this object kappa falls within the frame of Finsler geometry, but with the one wrinkle that we have very low regularity for the pseudometric. Okay. So here's a baby example that probably everybody knows, but I'm stating it here for two purposes. One is that this is the one example that I can present completely. I can actually give you a formula for the Kobayashi distance. In this case, the Kobayashi pseudodistance turns out to be an actual distance. I can do that. And also probably this is the foundation to talk about one of the motivations of this work. So I start out with the upper half space model of hyperbolic space. So it's pretty trivial to see that the Kobayashi metric in this example is given by this formula. I take the Euclidean length of a vector and divide by the distance from the real axis. It very easily follows, it's just a computation, that vertical line segments are geodesic segments for the Kobayashi distance. And furthermore, the relationship between the Kobayashi distance and the Kobayashi pseudometric, that is, one is the distance is the integrated form of the metric, actually reveals by this formula that any holomorphic map that preserves the real line actually is a Kobayashi isometry. So in particular, Möbius transformations that fix this real line will do. So we have this other set of geodesics. So these circles, semicircles in blue are images of geodesic lines. And I can actually jazz up this argument that I stated, which is start out with this formula, use the fact that the distance is the integrated form of kappa, and this the argument of moving things around using Möbius maps that fix the real axis actually shows us that I might be off by a constant. I might be off by a constant, which is unimportant. But the Kobayashi distance between any pair of points, now not necessarily lying on a vertical, is given by this formula. So this is the modulus of the logarithm of a certain cross ratio. Okay, where these objects q infinity and p infinity are the endpoints of any Euclidean half circle passing through the points p and q. So endpoints as in points sitting in the real line. Now, if you look at this, so once again, here is a statement which is pertinent to the theme of this conference, in that this will remind you of the Hilbert metric on convex domains, with the interesting difference, and that is that lines in convex domains are replaced by these semicircles. With that distinction, this is precisely the Hilbert distance rewritten for hyperbolic space. And in fact, I must mention that all of what I'm talking about represents joint work with Andrew Zimmer, and one of the results in here is joint work with a PhD student of mine, Anvoy Moitra. So Andrew Zimmer's motivation for what I'm going to talk about actually came from this observation, made in a more subtle fashion by Yves Benoit, that there are all these analogies between the Hilbert geometry and Kobayashi geometry. And so presumably there is this wealth of questions associated to Kobayashi geometry that one could ask and seek to answer, which are analogs of facts in Hilbert geometry. Now, my own motivation the motivation that brought me to this project was slightly different, in that I was more interested in what negative curvature interpreted in a weak sense could do to outstanding questions in complex geometry, in Kobayashi geometry. And in particular, my interest was when is it that bounded domains in Cn look like this? So the question is, well, what does this mean, right? So let's clarify. So I want you to keep in mind how these geodesic lines, I want you to observe how they sort of bend into the bulk. So this brings me to a notion of visibility that a lot of you are familiar with, and I realize I should probably go back and begin with, in the Riemannian world, by introducing, well, I don't have to introduce, I think everybody here knows what a geodesically complete Riemannian manifold with non-positive sectional curvature is, recapitulate how these manifolds admit what's known as a visual boundary, and then if I have an object of this kind that has pinch negative curvature, then one establishes a certain property known as visibility, whatever that is. We shall see it in a moment. But remember that the Kobayashi pseudometric in the setting that I am interested in, or let's just say Kobayashi metric, if I have bounded domains, these are true metrics. Kobayashi metric is a Finsler metric, but with really poor regularity. So the better place to seek an analogy to what the word this that I uttered a couple of minutes ago, a better analogy would be actually to look at the geometry of metric spaces. So I want to discover what I mean by visibility in this metric space, bounded domain in Cn equipped with the Kobayashi metric. And a nice place to look for an analogy is actually to look at a slightly rougher setup. And these are the cat minus k spaces. it's nice that there are many metric geometers in the audience, so I can actually speed through, and if anyone is really not familiar with what's coming, the purposes of talking about cat minus space, cat minus k spaces is merely for the purposes of analogy. I'm actually going to just talk about cat minus 1 space. So these are spaces where which are defined in terms of comparing the local geometry with the geometry of a model space. And a cat minus 1 space is a geodesic metric space, which is to say that given any pair of points, there is at least one geodesic segment connecting these, and such a space is called a cat minus 1 space if it has the following property. For each geodesic triangle in the space, in the metric space X, and a comparison triangle, which I'm referring to by capital letters, lying inside hyperbolic space, the example that I gave a couple of slides back. Now, because of negative curvature, I don't have to worry about the existence of this comparison triangle. It will be there. It is a triangle such that if I go with, if I look at a geodesic triangle, little a, little b, little c, there will exist a comparison triangle in hyperbolic space. So remember how the geodesics look like? So this here is a comparison triangle in hyperbolic space, A, B, C, such that corresponding sides have equal length. So little a to b is equal to this edge here. The edge little a to little c is equal to this edge here, and little c to little b is equal to this edge here. So probably I should be a little careful. I should do this. Yeah, this is correct. Then, if I pick any pair of points on the triangle I'm interested in, then the length of the geodesic line will be less than or equal to, so advance the slide, then the length of the geodesic line will be less than or equal to the corresponding length. So I should be marking this correctly. So this here is capital X and CB. This here is capital Y. Then this length dominates this length. And this is actually true for any pair of points in here. So you see, this is sort of a notion of negative curvature, because what it is saying is that geodesic triangles are thin. And how thin? They are thinner than corresponding triangles for the comparison space. So that's the whole idea. And okay, so let's take a non-compact geodesically complete. So I have geodesic lines passing through any point, geodesically complete cat minus 1 space. Then we can actually construct this boundary at infinity. So I fix some base point. And I look at the set of all geodesic rays that issue from the base point little o. And then I define this equivalence relation, which is why I would go with this is pretty obvious. I require two geodesic rays to be equivalent if the distances of corresponding points on each such geodesic ray is bounded, but is uniformly bounded. Of course, you might be wondering, okay, well, what the hell? I have this geodesic ray. I could reparameterize one of them. It is understood what I mean here is the time one parameterization, the unit speed parameterization, or the arc length parameterization. So I look at this collection of equivalence classes, and this is called the visual boundary. what is a lot less non-trivial is that I can topologize the union of the space X together with its visual boundary in such a way that I have a compactification. So this X continuously embeds into X bar, which is now compact in a continuous fashion. Okay, so this was sort of a whirlwind tour through cat minus k spaces, and this is what we have. What I want to call visibility in the setting of today's talk is something that I'm going to abstract from a theorem that I shall state, standard theorem in Alexandrov geometry. So I have X is a non-compact, geodesically complete cat minus 1 space, and this minus 1 parameter isn't important. As long as I have a cat minus k space, the conclusion will follow. I pick any two distinct points in the visual boundary, and I look at any pair of strongly disjoint neighborhoods around the 2 points at infinity. This is what I mean by strongly disjoint. Then, in fact, for any pair of for any geodesic ray at all that originates in one of these open sets and terminates in the other, I can find a compact set. So I've stated this in the wrong order. I can actually find a single compact set which depends on all the parameters chosen above, such that any geodesic that issues from the neighborhood U zeta and terminates in the neighborhood U eta intersects this compact K.
So you should replace compact with bounded.
Beg your pardon?
Replace compact with bounded.
Oh, yes. I should actually say bounded. Thank you. That's actually important because let me draw a picture. So this here is the visual boundary of X, and I pick up a pair of points, and I actually have. So there's this further data that I want. I want a pair of strongly disjoint neighborhoods, and I want this bounded object. So the key thing is this object is far away within the bulk, and any geodesic that issues from here and winds up in this other neighborhood must bend into the bulk. So this is the picture I want to abstract, and this is what I'm going to call visibility, but with a few differences, because I now want to get back to the setting of bounded domains in Cn. So there's this theme that is actually rather fruitful as long as I'm staying in the framework that I have some reasonably nice ambient space. In this case, I'm focusing on Cn. The correct analog in a more general setting would be some Stein manifold. And I look at a relatively compact connected subset thereof. There's this very fruitful idea of looking at the intrinsic geometry and playing it against the extrinsic geometry. We saw facets of this in the very first talk in this conference. So this is a rather fruitful point of view, and I'm going to have this picture in mind, but I'm also going to have the interplay of the intrinsic and the extrinsic geometry in the definition that I'm going to formulate.
Excuse me. This picture, just for the history, if I'm not mistaken, in this Bishop O'Neill paper 69 on visibility manifolds and other things, they used to call this is strong, not weak, they used to call this uniform visibility.
Uniform visibility, yes.
And it happens that it's equivalent to Gromov hyperbolicity. for Artstein-Avidan than for...
Exactly. Yes, absolutely. Yeah, so I knew someone would bring this up, which is why I sort of had this disclaimer that I probably should have started with the Artstein-Avidan theorem. But yes, you're absolutely right. Thank you. Yeah, so now there's one horrible technical problem that arises, which I need to be able to deal with in order to make any sense of this picture. And that is, even if I have a domain omega such that the Kobayashi distance thereon is a true distance, we do not, this is 2018, and yet we do not know whether this metric space is in general a complete metric space. So we have a slight problem in that we don't even know whether, given any pair of points, I have a geodesic for the Kobayashi distance linking them up. So I have that problem. And I certainly don't know if there are geodesic rays. So there is this technical problem that needs to be handled. So I want to actually introduce a notion which rectifies this deficiency, which is this notion of what we call lambda kappa almost geodesics. So let's see, there should be an eraser somewhere. Yes, here we go. So sigma, this is a map from an interval in the real line, could either compact or non-compact, into omega. This is a lambda kappa almost geodesic so there are a bunch of properties. So I look at the usual distance, I look at the Kobayashi distance between sigma t and sigma s. Well, this is less than or equal to lambda times the distance between s and t, but with a bounded error. So this is the kappa parameter, and the analogous thing on the other side. So I have a 1 over, so this thing is dominated by 1 over lambda times s mod s minus t minus kappa for all st. So this would be a quasi-geodesic. But quasi-geodesics don't even have to be complete. This doesn't guarantee complete, don't even have to be continuous. I also want this additional property, which is that sigma is absolutely continuous. Right? Which means almost everywhere I can talk about the tangent to sigma. And kappa, so this is a different kappa, this is the Kobayashi metric. Kappa omega at sigma t, comma, sigma prime of t. So this is the length measurement for the tangent is less than or equal to lambda for almost every t, right? So if I have these two properties, then I call this sigma a lambda kappa almost geodesic. Okay. So this is this little technical wrinkle that we have to go through, but then, occasionally it's a just world because these chaps do exist. So if omega, and I don't need any additional properties of omega, as long as I have a bounded domain, boundedness is kind of important, then for any kappa positive and for any pair of points, there exists a 1 kappa almost geodesic connecting the 2 points. And therefore, for any lambda greater than or equal to 1, I do have existence of lambda kappa almost geodesics. So here's where the Finsler angle comes in. So it's kind of unfortunate that, there's just so much one has to say about the circle of ideas. But you remember I had mentioned that the original definition of the Kobayashi pseudodistance is not that you integrate the Kobayashi pseudometric. Now, given with the original definition, which depends on constructing a chain of analytic disks connecting a pair of points, I can actually find a C1 smooth path from x to y, such that the arc length reckoned in the Kobayashi metric is only slightly worse than the actual Kobayashi distance between them. Okay, so that's what gives me my bounded error. And then, so this is actually, I can actually find a C infinity smooth curve that does this. But then I want a lambda kappa almost geodesic, so I then have to reparameterize by arc length, and that kind of screws up the regularity. So really briefly, that's the existence proof right there. Okay, so so now going back to that picture that I erased. So definition: if omega is a bounded domain, we say that omega is a visibility domain with respect to the Kobayashi distance. So I'm sort of picking up the language in Bishop and Eberlein. So I'm dropping the term uniform, which so they have sort of two flavors of visibility. I'm sort of dropping the adjective uniform because this is already a rather long phrase, but uniformity comes from this uniform choice of K. So I say that I say that omega is a visibility domain with respect to the Kobayashi distance if for each lambda greater than or equal to 1 and kappa positive for each pair of points on the topological boundary. I don't need to go through the construction of the visual boundary. I just pick a pair of points in the topological boundary, and for each pair of omega closure open neighborhoods around these points, zeta and eta, such that the closure of these neighborhoods are disjoint, there exists a compact set inside omega. This is not a compact in omega closure, compact inside omega, such that the same conclusion as in the previous slide holds true. For any lambda kappa almost geodesic that starts out in omega zeta and ends up in omega eta, the image of this almost geodesic intersects K. All right? So we get the same picture, but with this technical wrinkle which we need because we don't in general have geodesics. Okay, okay, that's the definition, but then how do we determine if any domain is a visibility domain for the Kobayashi metric at all, right? So that therein lies the question. So some notation. So this delta sub omega will simply be the Euclidean distance of a point z in omega from the boundary of omega. I'm going to talk about what the geometric meaning of this is in a moment. But this is the supremum of the, so I have this real positive parameter r. M omega of r is the supremum of the reciprocal of the Kobayashi metric at z for the vector v. And I supremize over all z that are within distance r from the boundary, and over all vectors of unit Euclidean length. So, this is some measure of how small the Kobayashi metric can get on the Euclidean sphere, on the round sphere. Okay? So here is actually a general visibility lemma. This is an analytical condition And you can just subject your domain. If I give you an example, you can just subject the domain to the following test. So I have a bounded domain. Suppose various things exist. There exists a C1 smooth, strictly increasing real function, such that I should actually say non-negative here. But that would follow from what I would say next, such that this function, in fact, is not merely strictly increasing, but it blows up as you approach infinity. And then for some z0 in the domain omega, the Kobayashi distance between this fixed z0 and an arbitrary point in omega is dominated by little f of 1 over delta omega at z for every z. Assume that this guy decreases to 0. So please note, it's kind of evident that this is a function that is increasing in R. Look at what we are supremizing over. So assume that as you approach 0 from the right, m omega of t decreases all the way to 0. And assume this analytical condition. If this be the case, then omega is a visibility domain with respect to the Kobayashi distance. So now the question arises, well, I mean, this is certainly a very quantitative test. So one could presumably test a whole lot of domains to be able to say whether this is a sufficient condition. So you can't say whether a domain is not a visibility domain, but you can certainly determine if a domain is a visibility domain. It's a very general test, but you must be wondering, where on earth does this even come from? How would you even dream this up? So just hang on a moment. Let me just write down something. So please note, there is actually nothing special about this point z0, because if I have this condition, then by the triangle inequality, I can find a different function that depends on the altered base point, which wouldn't affect the integrability condition. Okay, so there isn't really a issue of choice here. But let me just write this down before we lose this to the next slide. So I want the integral of m omega over r over something singular times f prime of 1 over r. So I want this function to be integrable near 0. Okay, let's put this up and then I wonder where this comes from.
Excuse me, so what is the norm you're using in the definition of m? Because v is norm 1.
So this was the Euclidean. So this is the Euclidean norm.
But it's arbitrary.
Beg your pardon?
It doesn't have an intrinsic meaning.
Oh, it doesn't have an intrinsic meaning, but what would happen is that there is a connection between this norm and this delta over here.
Oh, yeah.
So what would happen is if I scale this up, then that would affect this quantity here, and they balance out. Yes, right. Yeah, so probably I should have mentioned that there is a sense of making a choice both here and there. But these are actually only illusions of choice. Right. So the way this came about is, remember, there were these two motivations. Andrew's motivation for investigating analogs of phenomena in Hilbert geometry in the realm of Kobayashi geometry. Then my motivation was, having in hands a weak but not too weak notion of negative curvature, so that we could have certain applications to applications, or so that one would be able to answer certain outstanding questions. Now, the application I'm going to present to all of this today is not the one that motivated the two of us independently of each other. But I'm not talking about that application because it again requires a series of definitions. I didn't know that Andrea would actually talk about Kobayashi extremals and complex geodesics, because then I would probably be able to talk about this application. I'll just sort of leave it at that, but you'll notice.
Sorry, before you continue, can you give some examples?
Yes, I'm coming to that. The next slide is examples. Yes. Because this, I mean, even this condition is super mysterious, and one would appear to be borderline insane to be able to dream this up. So, I mean, why did we dream this up? Where does this come from? So you'd notice there are two pairs of authors here. So Zimmer and I were motivated by certain very concrete questions. And based on work that he had done and work that I had done somewhat independently of each other, we came up with a condition that guarantees visibility in this sense. But then Moitra and I were interested in seeing if we could broaden the envelope of examples. And we realized that there's this more general condition that actually does what is needed. So examples. So we say that a domain is a Goldilocks domain. Okay, so now these are, I think, very recognizable conditions. In fact, hyperbolic space has this property. So if I pick any z0 in omega, then there exists a pair of constants c and alpha, which depend on this base point, such that the distance between z0 and z is less than or equal to c plus alpha times the logarithm of 1 over delta omega. And there exists, the second condition is, so please note there's no involvement of stuff going on here in the second condition. But let's try to understand, this is actually geometrically, at least I maintain this is geometrically more revealing. Because note that 1 over m omega is the lower bound on the shortest. This is shortest reckoned in the Kobayashi sense. Shortest vector in the unit sphere bundle on omega at base points that are at distance at least r from the boundary. Oh, sorry, at most r from the boundary. So this second condition, in some sense, dictates that the Kobayashi metric does not grow too slowly as z approaches infinity. Whereas this clearly dictates that kappa sub omega doesn't grow too fast. Now, this geometrical perspective is actually very useful because it gives us a whole bunch of examples. I unfortunately don't have the time to go into the proof of why these are examples. Well, but strongly convex domains. So these are smoothly bounded domains where the second fundamental form is strictly positive. So strongly bounded, strongly convex domains, these are sort of the simplest to see. Now, this actually uses some fairly deep theory. But a pseudoconvex domain of finite type is a smoothly bounded pseudoconvex domain such that the order of contact that germs of analytic one-dimensional varieties make to boundary points are bounded from above. So that's what we mean by finite type. Now the important thing is these are legitimately a legitimately broader class than the class of all strongly convex domains, because by this famous example by Kohn and Nierenberg, there are examples in this class that are non-convexifiable. And then going back to convex domains, we can also show that convex domains with not necessarily smooth boundaries that have points of infinite type, provided the boundary isn't too flat, are also examples of Goldilocks domains. So the way we sort of discovered the most general visibility lemma was by looking at these conditions, which sort of emerge from work done independently by Andrew Zimmer and by me. And you note that this, if I take this as my example of little f, then this just transcribes to this condition, okay? So, so this comes from the fact that the derivative of the logarithm is log of 1 over x. The derivative of the log of x is 1 over x. So this chap here gives me a copy of r in the numerator, which cancels out to get this, right? So in other words, there's actually an enormous range of examples, which was actually a bit surprising to us. And the point is, in complex function theory in several variables, this is sort of the broadest class of domains on which one has very general results, and these are all sort of included in this Goldilocks category. You can kind of see why we call these Goldilocks domains because of this property here, that the Kobayashi metric doesn't grow too slowly. But now if the Kobayashi metric grows too fast, then that would make this chap grow terribly fast, but we don't want that either. Now, so time is ticking away, so you know what, if you have questions, then while you're asking me questions, I'll sort of flash this slide in the background. But the point is that these conditions actually censor domains whose boundaries have points of infinite type in this sense, points where this property is negated, where the boundary is far too flat. This also negates, this is a statement that is dimension independent. So take your favorite domain with a pointed cusp, and you will not get this property. So this censors out domains that have sharp outward pointing cusps. Inward pointing cusps are good, or boundaries that are too flat. So that general visibility lemma was a lemma that we kind of needed because we intuited that this, while not, whatever this is, while not a Goldilocks domain, still is a visibility domain for the Kobayashi metric. So this is the one application I want to talk about in the next 5 to 6 minutes. Okay, so let omega be a taut Goldilocks domain. Now, what do I mean by taut? I'm going to come to this in a moment. Now, if I have a holomorphic self-map, and I look at the iterative dynamics of this map, then there is this sharp dichotomy. Either all orbits are relatively compact. Well, if any one orbit is not relatively compact, then in fact, all orbits will converge to a single point on the boundary called the Wolf point. Now, this has a history. So we call this a Wolf-Danjois type theorem because for omega equal to the unit disk, this is a really classical result. And things kind of remained at this state for many, many years, and there was this breakthrough by Marco Abate, one of the organizers of this event, who extended this to strongly convex domains in any dimension. Then Mercer improved on this, essentially using the same technology, to convex domains where the boundaries are allowed to be a little flatter, but not so flat that you have arbitrarily high orders of contact between analytic varieties and the boundary. So in other words, finite type domains. And then Abate and Raisi relatively recently kind of had probably the most general result that one has for convex domains. I must mention that when we are convex, we have a stronger dichotomy, in that the dichotomy is there is a fixed point or this happens. Now, morally speaking, this is something that you should not expect when your domain is non-contractible. And if I have a pseudo-convex domain, in general, they don't need to be contractible. So if you have a non-contractible domain, there will be, morally speaking, there would be several fixed points, whereas our dichotomy says either every orbit approaches a fixed point or a Wolf point. So morally, we would have only a weaker dichotomy if we are not contractible. But in fact, implicit in Huang's work, who actually adds another line to this list, but since it's a little technical, I'm not putting it in there. Implicit in his work is the fact that the stronger dichotomy for convex domains would fail. So this is in fact the right level of a dichotomy. So very rapid tour through the proof. I'm just going to skip the comment above and make a comment about Gromov hyperbolicity, in that while we have sort of defined this notion of visibility by analogy, the analogy takes us only so far and no further. For instance, if I could show that the domains in the previous theorem were Gromov hyperbolic, then the proof of that result would follow by what's by now a standard argument. And in fact, I could actually do this for Kobayashi 1 Lipschitz maps. Holomorphicity wouldn't really be crucial. But Zimmer's work actually shows us that there exist convex Goldilocks domains that are not Gromov hyperbolic. So the two notions are not inclusive of each other. There are domains that are visible in our sense that are not Gromov hyperbolic, and there are domains that are Gromov hyperbolic but fail to be visible in our sense. So sort of whirlwind tour through the proof in maybe. Am I out of time?
Yes. We started late.
Okay. All right. Okay, but I should ensure that people don't miss their lunch, so maybe just a couple of minutes. So we assume that the first part of the dichotomy does not occur. So assume that it isn't the case that every orbit is relatively compact. Okay, so check. This is classical. I need Montel's theorem to be able to extract convergent subsequences from the sequence of iterates. And the Goldilocks property actually tells us that what these convergent subsequences in fact converge to are constant maps that where the constants sit on the boundary. So if I look at the closure of this in this class of maps, the closure of the sequence of iterates in the compact open topology, and I remove the set of iterates themselves, what I get is a non-empty set of points in the boundary by this assumption. So I'm going to aim for a contradiction, and I'm going to assume that this set is of cardinality strictly greater than 1. And we'll see where that takes us. Okay, so here's case 1. Which is that if I fix some point and I look at the limb soup of the distances from the iterated image of that point from the point itself, let's look at the case when this goes to infinity. Well, then I can extract a sequence of indices so that these two properties simultaneously hold true, right? So what I will do is, by the fact that this sequence of indices goes to infinity, I would be able to find a strictly monotone sequence of these guys, and then extract a further set of indices to assume this, and then use Montel's theorem to get this last line. Okay. Now remember, we have this assumption. So there is this other subsequence of iterates which converges locally uniformly to a boundary point. So I have these two. So now here's where visibility comes in. So what I'm going to do is I am going to look at a sequence of of, oh yes, having picked this second sequence, I will pick a further subsequence of these so that the sequence with the label n is, the subscript with the label n is greater than the subscript with the label m. We'll see the reason for this in a minute or so. So I now look at 1-1 almost geodesics that join this point, this point in the orbit to this point in the orbit of x. Okay? Since zeta and eta are distinct, visibility actually gives us a constant r, such that the Kobayashi distance from the fixed base point to at least one point on each geodesic is bounded by a uniform r. Okay, so let's keep this in mind. Okay, so now because these points are joined by a 1-1 almost geodesic, well, so this first line is just a triangle inequality, right? And then this comes from the definition of a 1-1 almost geodesic and this estimate. So I get this estimate, okay, which now given, so this is something that Andrea had mentioned, that the holomorphic maps are contractive with respect to the Kobayashi pseudometric. Ergo, the Kobayashi distance, so holomorphic maps are contractive with respect to the distance as well. So this is, I just call this a Schwarz lemma. What I mean is this is applying the contractive property over and over again. Okay, so I get this. Okay, but we are very close to a contradiction. If you shuffle around terms in equation number 1, then I have this sense that there is a point sufficiently far along down an orbit of an iterate that that is not going to stray too far away from x. But then let's look at where are we? Yeah, but let's look at this inequality. So this is supposed to be small, but then remember these are actually going off to infinity. So we have a contradiction. Now there is this case too, and I'm not going to bother you with this because you see, if this were complete, then this damn thing would never actually arise, you know, because the boundary would be, the topological boundary would be at infinite distance. So this is one of those unfortunate things arising from the fact that this metric space, we don't know whether they're complete in general. But it's sort of the same intuition over there. So I'm going to end with the intuition that because of contractivity, points along an orbit shouldn't stray too far away from the initial point on that orbit. But then because of visibility, the distance between the limits of these two orbits is the sum of the distances from this x to the points in the boundary, but that's infinity. Therein lies, so that's sort of the geometric intuition which leads to a contradiction and hence the proof, and I'll stop right here.
So maybe just one quick question before lunch. Any questions or comments? Okay, so I guess people are hungry. So.
Oh, good.
Thanks. This condition reminds me of this